Hello wonderful person, this is Anton, and this right here is one of the Voyager probes. I don't know which one, maybe two, they look exactly the same. Now I wanted to start this video by possibly finding something around the house or possibly something my parents may have had that worked for a long time. The only thing I have that's relatively, I guess you can call it old, is this right here. This is actually a Geiger counter that you can use to detect various types of radiation, and I've used this in one of the previous videos where I tried to calculate how much radiation I was exposed to up there in the skies while flying in an airplane. And this thing is actually not even that old. It was actually bought in the late 90s, possibly 1999 or maybe 1998. So technically it's about 20 years old and it still works pretty well. It uses a few AA batteries, and by the way, this is totally not a sponsored video. It's just the only thing I could find that just still works after 20 years. Which is why this next segue should totally blow your mind. This beautiful piece of hardware has worked for 42 years in space, in these super inhospitable conditions, filled with radiation, extreme cold, and always bombarded by all sorts of miniature particles. So both Voyager 1 and Voyager 2 has been out there for 42 years and they still work. What's even more mind-blowing is that the scientists currently getting all of the data and studying all of the data, a lot of them, actually possibly most of them, were not even born yet when the probes were launched in around 1977. Now this video is obviously not really about how ancient these probes are. This video is about the fact that both Voyager 1 and Voyager 2 probes are technically now in the so-called interstellar space. Because NASA has just recently confirmed that Voyager 2, that was sort of lagging a little bit behind Voyager 1 because Voyager 1 is moving faster, has now officially reached what we would refer to as interstellar space, as indicated by its still functioning devices that we have that suggest to us that there is definitely an actual barrier between the so-called solar system and the interstellar space. And in this video I wanted to discuss some of these findings and to give you a kind of understanding of what's out there in the interstellar space compared to what's here in the solar system. But before we start, I'm sure a lot of you will probably ask what this long thing is here and why is it even there. Well, this is actually just a beam-like structure to separate the magnetic field detectors, the low field magnetometers as they're known. There's one right here and there's another one on the tip. And the reason they're in that location is to isolate them from the magnetic interference that might come from the craft itself. So that's really the only reason for this long structure. Also, this thing that's sticking out, that's the so-called RTG, or in more common terms, the nuclear reactor that's powering the probe. And we think that it's probably going to finally die somewhere around 2025. We're not entirely sure, but the probe probably still has about 6 to maybe 8 years left in it. Then right here you can see something shining. This right here in the middle, that's the super famous golden disk, also known as the golden record. It contains this information here, which basically presents a few hints about who we are as a species, and the location of the solar system right here is designated using the data from very well-known pulsars. This is in case anyone wants to actually find us. Maybe not a good idea, but now there's no way for us to ever get this disk back. It also has, as you can see, the sounds of Earth recorded on the disk. And in a sense, this is probably the most expensive record that we've ever created. And if we were to ever recover it, it would probably cost a lot of money. But anyway, then we obviously have a lot more sensors here and a lot of them still function, and this is how we were able to get all of this data about the so-called interstellar space. So what exactly have we actually confirmed this time? Well, so first of all, we've predicted that there was something known as heliopause. This is the kind of a boundary between the end of the solar system and the beginning of the interstellar space. And as you can see, it's sort of formed by the essentially sun itself. More specifically, it's formed by the magnetic field of our sun, while at the same time, it's formed by the interaction with the interstellar magnetic field, which is actually formed by various really highly energetic events, such as, for example, supernova that happen here, that do create magnetic field in the interstellar space. And what's interesting is that one of the main discoveries here was that both the solar magnetic field and the interstellar magnetic field are actually aligned with each other, which is something we didn't really expect to find. In other words, the magnetic north and south pole for both the solar system and the interstellar space seem to be aligned. And interestingly, in this graph that was presented in one of the papers that you can find in the description below, you can also clearly see that the strength of the magnetic field increased when the craft left the solar system space and entered the so-called interstellar space. It actually started increasing right around here, it was not a dramatic change, and then suddenly jumped when the craft entered VLISM, which stands for Very Local Interstellar Medium. And the difference in the magnetic field here is pretty dramatic. Now obviously this doesn't compare to the magnetic field here on planet Earth, but for actual space itself, it is a pretty dramatic difference. These numbers also seem to be different from the Voyager 1 probe that entered the interstellar medium a few years ago, suggesting that the actual helios sheath that is presented right here in this illustration is not uniform. It's more or less broken up in pieces and seems to have different strength in different locations. And what's even more interesting is that for Voyager 1, this event started happening at a distance of about 119 astronomical units away from the Sun, or 119 times the distance of Earth to the Sun. And for Voyager 2, this only started happening around 121 AU. So the actual size here was a little bit smaller than the size right here. In other words, the shape is not as uniform, it's more or less broken up into wavy little shapes here and there. And one of the explanations proposed so far is that it's very likely that this actual shape relates to the so-called solar cycles that last for 11 years. Basically, every 11 years our Sun goes from being very active to not so active, very active, not so active. Its magnetic field obviously changes as well, and this could influence the shape and the size of the actual heliosphere as well. And NASA used the analogy of lungs to try to explain this. Basically, imagine it's as if our Sun was breathing. When it's very active, it expands, and when it's not so active, it sort of shrinks in size. Which is probably what happens to the heliosphere, and this is what we were able to detect here when Voyager 1 and Voyager 2 passed. Basically, because of this solar activity, the shape itself changes quite a lot every 11 years, and it's probably why we observe these unusual discrepancies between two probes. Another really interesting discovery here came from the detection of the cosmic rays. It seems that as soon as the probes crossed the boundary that was created by our Sun, the amount of cosmic radiation increased quite a lot. In other words, it seems that the actual heliosphere protects our solar system from about 70% or so of all of the galactic cosmic rays that would otherwise strike our planet and our solar system. You can see in this graph how as soon as they crossed the boundary, the galactic cosmic rays increased in numbers, but the other heliospheric particles decreased dramatically. And all of this was detected about a year ago on November 5th of 2018. Now this is something that we definitely were quite surprised to find out, and is a really important discovery if we ever want to become an interstellar species. It simply means that there's a lot more galactic cosmic radiation out there outside of our solar system. And just to confirm that the heliosphere was not perfectly round as we expected it to be, the probe, as it was passing through this region, detected these unusual increases in radiation. You can see them right here, these two pockets, suggesting that there were certain locations inside the heliosphere where the radiation was essentially leaking, suggesting that the shape is once again not as uniform as we predicted it to be. Another way of looking at this as an actual boundary is by looking at the density of plasma. Plasma is of course any kind of a gas where you strip the gas of its electrons, giving it obviously a positive charge. Now in general, plasma is usually associated with things like fire or the sun itself, but in this case plasma also exists in certain locations around the solar system and interstellar space. So as both probes were leaving the solar system, they encountered a sudden density change, a very high density of plasma, and the increase in temperature of that plasma. As a matter of fact, it was really the temperature that surprised the scientists the most. When the Voyager 2 probe entered the location known as heliopause, that's basically the location right before the interstellar space, the temperatures here jumped to about 30,000 to 50,000 degrees Kelvin. That is really hot. Now obviously it doesn't mean that the probe is going to burn, because the density here is still pretty low because it's space after all, but just the fact that it was really hot plasma really surprised the scientists. Now, both the increased temperature and of course increased density were actually predicted by our models, but we didn't expect the density to jump so much and the temperature to be so hot. So this was a bit of a surprise. And all of these discoveries from Voyager 2 suggest to us that this is an actual physical barrier. It's almost like a wall of hot plasma and various types of radiation, cosmic radiation, that suddenly jumps up as soon as we cross into the so-called interstellar space. And don't forget, this is also the location where we've discovered some other objects, like for example, objects like Eris and Sedna are in these faraway regions, and this is also where we expect to find Planet 9. But as you can see from this graph, we're not even close to the so-called Oort cloud, where all of the comets come from. So it will still take a really long time, specifically actually close to about 400 years for us to reach that location. By then, both of the probes will be unfortunately dead. And as a matter of fact, the sad news is that this is probably the last time we'll ever hear about the probes. There's very little more for us to discover in this particular region of space, and the probes are really having trouble communicating with Earth. Even though the antenna here, as you can see, is pretty big, and as a matter of fact, it uses a very interesting technique of aligning with the sun by using the solar detector right there, and it's basically always pointing at the sun because of this. Nevertheless, because of the distances here, it takes about 16.5 hours for light to reach the probe, and any signal needs to be really amplified. And so because of the distances, we're just having trouble communicating with this and receiving the data. Within the next few years, it's very likely that the probes will fail and will probably become the remnants of the early exploration of the solar system. Maybe one day someone will discover these golden disks and possibly even find planet Earth, but it's not going to be anytime soon, because it will take thousands and actually millions of years for these probes to reach nearest stars. But that's not the last time we'll get to explore the heliosphere and the so-called interstellar space, because in 2038, assuming of course it still works, the beautiful New Horizons probe that took photos of Pluto will be also entering interstellar space and reporting back to us, telling us what it discovered in there as well. But unfortunately for both Voyager 1 and Voyager 2, that's probably it. It's very possible that we're not going to hear about them ever again until they shut down and NASA reports that it finally lost the communication with these two probes. And it is still kind of shocking that they even function after 42 years, but that's basically the power of human engineering and human ingenuity. We created something that lasted for a very long time in some of the most inhospitable conditions you can imagine. But on this somewhat sad note, that's all I wanted to mention. I wanted to kind of explain to you what we've discovered and how both of the probes are now in the interstellar space. Hello wonderful person, this is Anton, and remember this? This is Oumuamua, the object, or the so-called interstellar object we've discovered back in 2017 that made headlines around the world. Well, looks like we may have discovered another one of these rocks, but this time much bigger, much brighter, and going way faster. So since the original discovery back in 2017, we've learned quite a few things about Oumuamua, although currently we don't really have any means of studying it in a lot more detail. For one, we've realized that it's very likely not really this shape, specifically, it's probably not the so-called sausage or cigar shape, and it's definitely not a so-called interstellar sail like some scientists suggested. It's more likely to be this unusual disc-like object that's probably the best representation of what we were observing in terms of the actual light curvature that we were detecting. But forget about Oumuamua. This object is slowly moving away from us, we'll probably never catch it, and it's very likely we're not going to be able to study it much more. And here's what the trajectory of Oumuamua looks like in Universe Sandbox. You can see it passing very close to the sun right there, and now it's going to start slowly moving away from the central region, and this is already, I believe, January of 2018. And so in just a few years it's going to reach farther reaches of the solar system, and we're going to probably never really see it again. So it just so happens that the new object that was just recently discovered is kind of on the way to this inner system. It's actually still approaching the inner solar system, similar to what you see right here. This is still Oumuamua though, but the object we're looking at is currently being actively studied, and we're trying to see if it's really an interstellar object or if it's just an object that's moving too fast. First of all, here's what a video looks like. This was released only basically 24 hours ago from when I'm making this video, and you can sort of see the object is moving really fast across the night skies. And this was filmed and detected by a very famous observatory that's not often talked about, but it's an observatory in Crimea that is really famous for discovering a lot of minor planets and a lot of asteroids since 1966. It's been very active at producing a lot of newly discovered objects, and basically this is kind of what it looks like. This is the Crimean Astrophysical Observatory. And when it comes to the name of this object, at least currently, originally it was known as GB00234. GB stands for Gennady Borisov, the original discoverer of this object, and now it's sort of known as C2019 Q4 Borisov. So this might be the next Oumuamua, as long as it's of course confirmed. And by using this orbit simulator from orbitsimulator.com, I can sort of show you the projected trajectory. And so this here kind of shows you where it's going to pass. This orange orbit is Mars, so it's going to be somewhere between Mars and the asteroid belt, and this will be the closest approach at around 1.9 astronomical units, and it's then going to move away and leave the solar system, but it's currently coming to us from the direction of Cassiopeia, which is of course one of the constellations we have in the night skies, and it's sort of visible, and you can actually find it by going along the path of the Milky Way here. And I think it's somewhere right there. There it is. So this is the Cassiopeia, and essentially this means that this object is coming to us from a direction of the galactic plane. Now, we don't really know what star it may have come from. We basically don't really know much about it just yet. We need to really observe it for many days to determine its exact trajectory. Right now, we don't unfortunately know much about the trajectory of object that I guess we can refer to as 2019 Borisov. I'm sure that this is going to be a more appropriate name as we confirm this discovery, but right now this is all we know. So it's coming from this direction, it's moving relatively fast, it's about 30 kilometers per second faster than it should be. Essentially this is referred to as the excess velocity, and it's almost guaranteed to be a what's known as an interstellar object. Now as we observe it and as we take more videos and film it, we'll be able to see it quite well. As a matter of fact, this is very likely going to be one of the brightest such objects we'll see in a long while. And this is what's really surprising about this object, is that it seems to be a lot larger and a lot brighter than scientists anticipated. Now, we think that these objects are quite common, but we expect them to be much smaller and a lot more dim, a lot less bright. And this here will be quite visible even with most likely amateur telescopes. As a matter of fact, the discoverer of this object only used the telescope that was about 65 centimeters in diameter, and from what I've read, it seems that it might have magnitude of a typical asteroid, so it will be relatively easy for us to analyze its spectrum, possibly even determine what's on its surface, and very likely find out what elements it has on its surface, and then maybe even estimate where it came from. So all of this will be very interesting in the next few months. We're going to have a lot of studies coming out, and because it's still coming closer and closer to us, it's very likely going to give us a lot of new data. And compared to Oumuamua, it's even a little bit more hyperbolic. So in other words, it's moving a little bit faster and has a slightly more eccentric orbit than Oumuamua did. So even though Oumuamua was moving at a certain speed, and it was already pretty high, this asteroid seems to have a little bit more of everything. Size, brightness, speed, and, well, I guess in some sense, all of this data is going to provide for us in the future. Now, if you'd like to look at the actual data that's being currently collected and that's been officially published on the website known as projectpluto.com, here it is. It's also in the description below. And if you know how to read it, it's basically going to show you what we're learning about it. And all of the information here will be updated pretty regularly. And the best thing about this particular link is that there's a button right here on top that says Orbit Simulator View, which you click, and then you get to explore the orbit of the object itself. And then you can kind of zoom around here and twist things a little bit just to see where it is and its position in the night sky, so that maybe if you have a powerful enough telescope, you can try to find it yourself. Now, I don't really know if it's going to be that easy to find because it is, after all, a relatively small object, but it's possible that within the next few months, it might be just bright enough for us to see it with amateur telescopes. And by the way, Earth is right here. This is the blue ring, in case you were wondering. So it's not going to be close to Earth, but it is going to pass relatively close to Mars. Although relatively close is a relative term in this case. So here the distance, as I mentioned before, is going to be about 1.9 astronomical units, which is still pretty far away. It's basically double the distance of Earth to the Sun. But until more data comes out and until we learn what's really happening with this rock, where it's headed, and where it came from, all we can do is just maybe look at these simulations and try to figure out by simulating the trajectory and looking at it using computer simulations. Now, we don't really have much more detail about this just yet. All I know is that, well, here's actually the picture of the guy who discovered it. This is Gennady Borisov himself with his custom-made 65 centimeter telescope. And what's really interesting is that apparently, I guess he didn't really use the telescope from the Crimean Observatory and used his own instead. And from what I've read as well, it seems that he's already discovered at least 7 different near-Earth objects with this modified telescope. And although I'm not sure if it's his own telescope or if he's just using the facility where he built this, I guess the details of the story will come out once we start asking more questions. For now, the cool thing is that there are already several different telescopes actively looking in the direction of this discovery and trying to establish the specific details of, well, really everything. So in the next few months we're going to have a lot of really interesting things to talk about, and it's very likely that we're going to find a lot more of these objects coming from the various parts of the galaxy, and also possibly from the outskirts of our own solar system. And for now, that's all I wanted to mention in this video. Check out the links I mentioned in the description below, including of course the links with all of the up-to-date data. And if you do have a powerful enough telescope, you might be able to see this maybe in the next few months or so. On that note, I hope we come up with a really cool name for this. I really hope it's not just a number, because, you know, Oumuamua became famous because of the cool name that it had. Hello wonderful person, this is Anton, and this right here is the first picture ever of an actual black hole. Now, I know most of you have already probably seen this from the news or from some other source, because basically this right here right now is trending. For this reason, what I actually want to focus on is some of the things that need to be clarified, both about the image, the expectation versus reality, and the science that may have not really been explained really clearly in the press conference or by the modern media. So first of all, what exactly are we looking at? This, of course, is the actual event horizon and the plasma produced by the all sorts of matter that is falling toward the black hole and is creating this accretion disk. So essentially, we're sort of looking at this from maybe this perspective right here. And what we're seeing is the actual plasma from the accretion disk. And it just so happens that the actual prediction was very, very similar to this, but unfortunately for the scientists behind this study, their prediction was a little bit too good. It was too pretty. The expectation versus reality here, a lot of people not familiar with how this was done expected something like this, but instead, we got this beautiful pixelated image that was taken by a potato. Okay, this is actually not me talking, this is the comments that I've been receiving from people watching the press conference with me only a few hours ago from when I'm making this video, and many people were just disappointed at what they were seeing. A lot of the general sentiment was, is that it? This is what they were so excited about? And let me actually explain to you why you should be excited about this as well if you're not. Because of the way this was taken, and essentially why this picture does make a huge difference in the future of science. So first of all, this is a picture of the 200 scientists behind this beautiful and incredible study. They were coming from different walks of life and also from different countries, continents, and of course fields of study. And for the most part, they all had one goal. They wanted to create the incredible. They wanted to take a look at something really far away, something that we usually think has no light emitted from it, something that even Einstein himself didn't really think was real. And they decided to take a photo of it just because photography has reached its golden age. Everyone's taking photos everywhere, everyone loves selfies, and we needed a photo of a black hole. And to take this photo, they used these 8 telescopes from around the globe and combined them into one by essentially making sure that everything was timed correctly. They used very accurate atomic clocks in every location. They collected the data by looking at exactly the same spots in the sky, and then they also made sure to account for the rotation of Earth, which apparently someone at first didn't really think was necessary. But this was really important because that's the only way you can then combine all of this data and see it as if Earth was literally one large telescope or one single eyeball looking into the skies. And it just so happens that it totally worked. And we've now confirmed that this technique known as interferometry is literally the future of space observation. The resolutions that we are now able to see are going to be absolutely ridiculous. Now, most of us believe that this is going to be the picture of Sagittarius A star, the supermassive black hole in the middle of our own galaxy. But even though it is technically supermassive at a mass of about 4.1 million masses of the Sun, it's still not massive enough and is actually a little bit difficult to observe because the accretion disk here moves pretty fast. For a black hole, the matter in the accretion disk here moves approximately once per half an hour, and because of this, when they were looking at Sagittarius A star, they realized that the data was coming out a little bit blurry. You can actually see the recreation right here. This is from Goethe University in Frankfurt. And you can actually find more of their videos that are absolutely incredible in the description below. Their channel is really small, but they have amazing simulations. But anyway, so this right here is Sagittarius A star. And so this picture was even more underwhelming, unfortunately. And so they decided to focus on the picture of M87. And the galaxy M87 has really cool features. First of all, as you can see here, it has a ridiculously long astrophysical jet. And that's basically this thing right here that shoots out matter at almost the speed of light. And it just so happens that it's pointing almost directly at us. And this is completely by accident. Like, the chance of this happening is actually pretty low. But luckily for us, not really at us, but somewhere near us. And if it was pointing at us, we should actually maybe be worried a little bit. But anyway, so this is the center of this galaxy, and it's actually a very massive galaxy, about 200 times more massive than the Milky Way galaxy, where we live. And in this particular galaxy, right there at the center, there is a super ultra massive black hole. It doesn't have a name yet, even the galaxy itself doesn't have a name, but this is a very active black hole that's also known as the active galactic nuclei. And it's actually producing these super powerful jets that are shooting out a lot of energy. And also, because it's eating approximately 90 masses of Earth every single day, it's creating this very large plasma of accretion disk around it. And this is essentially what we're looking at when we're seeing this beautiful picture right here. We're seeing the actual plasma of the accretion disk. But as you can see, it's actually a little bit brighter on one side and darker on the other. And this is actually exactly what we predicted. We know that because of the actual velocities involved and also because of the actual gravitational effects from the black hole, the matter is slightly blue shifted or has more energy on this side, and it's a little bit red shifted on that side. In other words, when the accretion disk is looked at, this side on the left here is going to be brighter than the side moving away from us because of the red shifting effects and blue shifting effects. Since basically matter coming toward you has more speed and matter moving away from you has less speed. At the same time, we're actually obviously seeing the event horizon itself, and technically it's actually a little bit closer to the middle here because this is the region that I've described in one of the previous videos where you can't really have any more stable orbits. So the actual black hole is in the middle here. And it's a huge black hole. It's a tremendously big black hole that I'm going to show you in a few minutes compared to some of the objects you might be familiar with. So first of all, this right here, this Sagittarius A star, that's our own black hole, and it's about 40 million kilometers across. And let's actually use universe sandbox square to try to simulate this stuff. So here is the supermassive black hole that we have here. Here is our sun. We're going to place our sun right next to it just for a sort of a comparison. So this is basically our own supermassive black hole versus the size of our own sun. If I actually run the simulation right now, because of the tidal effects here, the sun is just going to completely fall apart and turn into the accretion disk almost right away. So let's not do that just yet until we compare it to the M87 black hole. And because this black hole doesn't exist in Universe Sandbox, we're going to have to create it from scratch. So first of all, let's actually move a little bit farther away here because it's going to be huge. And we're going to change its mass to the most recently corrected mass of 6.5 billion masses of the sun. Okay, there it is. It is ridiculously huge. It's actually already swallowing everything that I've just created. So we're basically inside of this black hole right now. There's Sagittarius A, there is the sun, and here is that tremendously large black hole of M87 with the radius here of approximately 128 astronomical units, which is equivalent to the distance, or about 3 times the distance of Pluto to the sun. So let's maybe one more time place our own supermassive black hole right next to it. So there it is, this tiny spot next to it. And then let's also place our own sun for comparison. So basically that tremendously large darkness that you see in the distance there, that's M87, and that's what we were looking at. And because of its size, this black hole is actually the second biggest black hole in the night skies after the Sagittarius A star. And this is why we decided to look at it. It's an ultramassive black hole, so large that technically it's about the same size in the skies, maybe a little bit smaller compared to Sagittarius A star. Now, as I mentioned in the video I made a few days ago, when we were looking at Sagittarius A star from Earth, in terms of size, it appears to be around the same size as a small apple, or I guess a small ball about 2 inches, placed on the surface of the moon. So if you were to go on the moon, place the tiny ball there and leave it there and then look at it from Earth, that's what we're looking at. But this here, M87, is even smaller. It's maybe about 1.5 inches in size. So it's actually really difficult to see these objects, but because of the way we did this by looking at it from different telescopes and then combining all of this into one single data set, that's essentially how we were able to discover and to create this beautiful image. Now actually, while we're looking at this picture, I wanted to mention one more thing. First of all, I'm really sorry I don't really know your name, wonderful person, but you're clearly very happy to analyze all of this data. But second of all, this right here is the reason why it took over 1.5 years to produce this image. They were struggling to actually transfer files. The files here were so large that it was impossible to transfer them via internet. They had to physically pick up the hard drives, as you can see they have a little handle here, and bring them all together into the same spot and then analyze them there. At the same time, when this particular telescope in Antarctica was added to this study, it just so happens that the weather there got so bad that it was even impossible to leave this location. And so the files were actually stuck here for a very long time until they were able to pick them up a few months later. And this is actually why it took so long to finally be able to combine all of this data, analyze it, produce it, and release it on April 10th of 2019. Now, honestly, it may still not seem like a huge discovery, but it really is. First of all, it's because of the fact that this right here is just a prediction. This is what we predict scientifically to be happening there right now. And because of what we saw physically, it actually confirmed everything we knew about the science of black holes, everything we knew about the universe. In other words, what we believed scientifically, what Stephen Hawking was saying, what Einstein was saying, everything they were predicting is basically absolutely correct, and that is just mind-blowing. It is mind-blowing that we're able to see an object so massive, so large, but so far away. The distance here is about 53 million light years away from us, which is about 1,000 times more far away, or about 2,000 times actually more far away than the closest supermassive black hole, that's our own. So in other words, that tremendously large M87 black hole is really far. And we were able to construct the models, we were able to predict everything and then confirm it scientifically by literally observing it. And that right there is where your mind is supposed to be blown. And if it still hasn't, it's probably because as of today, this is just more of a proof of concept. We're trying to understand how the universe works, but we're also trying to discover these techniques that will actually allow us to study and understand the universe around us with a lot more accuracy. And this is just one of those proof of concepts that has finally resulted in an incredible discovery. And because of this one right here, April 10th of 2019, is probably going to be one of the most exciting dates for the next few decades. Everyone is going to remember this day as that one day we were able to finally see a black hole. Now, two more things I wanted to mention here. First of all is, so Here, this is the M87 black hole. The actual size of the accretion disk across here is about 0.4 light years. This is a ridiculously large accretion disk, way bigger than the one around Sagittarius A star. The velocity here is about 1,000 kilometers per second for the actual accretion disk, and it takes about 2 days for this matter to move around the black hole. And because of this, it was much easier to see the stuff around this black hole than the one in our own galaxy. This is actually why they decided to release M87 picture as the main one, and Sagittarius A star was actually a secondary picture released through the studies. And at the same time, as I mentioned, the astrophysical jet here is produced because this black hole eats up about 90 masses of Earth every single day. And this, of course, is the accretion disk itself. And the jet itself is also very long. This is about 5,000 light years, and that's a huge distance. That's actually about 1/5 of a distance to the supermassive black hole in the middle of our own galaxy. And at the same time, if we actually look at the galaxy itself, the galaxy M87, it doesn't really look that special. Well, it's an elliptical galaxy. It's very massive, one of the most massive near us within about 100 million light years, but doesn't have any unique sort of shapes sticking out or anything that makes it different from other elliptical galaxies. But it is a very active galaxy, and one of the reasons we even know about this is because it's an extremely bright radio source. So we can actually relatively easily detect the radio waves coming from the center of this galaxy because it's active. It's an active galactic nuclei that produces a tremendous amount of energy. And the fact that this was a very powerful radio source was confirmed back in 1966 by the US Naval Research using these beautiful rockets that they were launching back then to test various theories. And so this right here discovered that this is a very powerful radio source, one of the most powerful in the night skies actually. So if you have a powerful enough radio telescope, you can easily detect it. And this is exactly what we were doing just now. We were using radio telescopes to look at it, but we wanted to see the center in a lot of detail. And what you see right here is the result of this. This is of course produced by radio telescopes, then converted to actual color. Hello wonderful person, this is Anton, and in this video we're going to be talking about new research and a new paper that seems to suggest that basically everything in the universe is connected. Literally, connected through a very unusual but currently somewhat invisible filament. So when it comes to stars and constellations and of course galaxies, we do know that many of them are somewhat connected to each other gravitationally. Like for example, if we were to find one of the typical globular clusters here in the Milky Way galaxy, we would find ourselves in something that looks like this. And this is basically a gravitationally connected structure where all of the stars and all of the neutron stars and black holes and everything in the middle here is connected and moves together and never really separates from one another. These are pretty much everywhere around the universe, and we've seen quite a lot of them in our own galaxy. But on much larger scales, we obviously get other gravitationally connected objects, and I guess the most famous one would be this, the galaxy. But it obviously does not stop there, because we've in the last few decades discovered that even galaxies connect to other galaxies. More specifically, the Milky Way, for example, connects to its satellites and to some extent to the Andromeda as well. So basically the Andromeda galaxy, the Milky Way galaxy, and all of the nearby satellites like the Large Magellanic Cloud, the Small Magellanic Cloud, or even this right here, the diffuse Sagittarius spherical galaxy, all of them are connected to the Milky Way through these somewhat invisible but nevertheless present gravitational links, and in most cases we even have actual signs of those links being formed. And you may have seen one of my previous videos about the Magellanic Bridge and the Magellanic Stream. Both of these are actually separate connections between various galaxies. So this right here is a connection between the Large Magellanic Cloud and the Small Magellanic Cloud, which are these two largest satellites of the Milky Way. This right here is the large, and right there in the corner right here is the Small Magellanic Cloud. And they do have a connection, and we've seen it several times now. And also these two galaxies have an actual gas connection to our own galaxy, which unfortunately is not shown here. So in the video that I made a few months ago, I did explain how all of this has been found and how we now know that this connection is actually physical. There are even stars between these galaxies that are formed in this gas. But then as you start looking at the larger scales, you get something known as the local group. The local group of nearby galaxies looks something like this in 3 dimensions, and the Milky Way is right there, this tiny spot in the middle, with these satellites being here, and the Andromeda and the Triangulum galaxies being right here. All of them also have their own satellites. This is also gravitationally connected, and we have actually found links, physical links that connects them as well. Now, today most scientists believe that all of this is sort of propagated through the mysterious dark matter. And there are quite a lot of various evidence that suggests that this is actually true. But it doesn't end here. If you were to zoom out of here even more, you would discover an even larger gravitational connection, forming first a cluster and then a supercluster. This supercluster that we are in is known as the Virgo supercluster. It's actually this right here, and you'll notice that there's this yellow formation. That's the largest gravitational structure we've discovered to date, and it currently has a name. It's known as Laniakea. The Laniakea supercluster is essentially the extremely large gravitational structure that has been reported by using this image right here, and I've also made a video about this explaining what exactly this shows in the past. But the idea here is that, so this is literally an actual structure. It's a physical connection between galaxies, but it also does not stop there. As we just discovered, especially in the recent paper that came out only a few weeks ago, there seem to be even more mysterious connections out there. Something that scientists currently have no idea how to explain, but they do seem to suggest that the connections are even more profound than we previously thought. And in this particular paper coming out of South Korea, what the scientists discovered is that when they looked at the galaxies nearby and compared them to the galaxies that are actually much farther away, specifically roughly around 20 to 30 million light years away from the Milky Way, which would be equivalent to maybe this distance right here. So the galaxies at this distance all seem to also have a very unusual connection that was detected in a very unusual way. So when the scientists behind this paper looked at essentially properties of galaxies, they noticed that many of those galaxies were actually moving and spinning in a very similar pattern. So when they looked at certain galaxies in one direction, they noticed that those galaxies had exactly the same spin and were, for example, moving away from us. Then they looked at other galaxies in a different direction and saw the opposite effect. Those galaxies were moving away from us and also spinning in a different direction as well. And their spins and their motion was actually correlated, as if something was mysteriously causing them to move and rotate in a very similar fashion, even though they were really far away from one another. So at this distance here, there was some sort of a mysterious force causing these galaxies to behave in a very similar way, and it can't be just explained by galactic gravitational forces. It has to be something else. And one of the suggestions and one of the explanations so far is that it definitely has to relate to something known as the galactic filaments. The video about the filaments should be popping up somewhere right there, but essentially, in a nutshell, what this refers to are these formations that you see right here. This is from the beautiful Illustrious project, which created one of the most realistic, if not the most realistic, simulations of a universe. And this simulation of the universe shows us that there have to be these very unusual formations, these filaments, that are formed by the combination of this blue stuff that you see here. This is the dark matter, mixed with the actual gas that forms stars and obviously other objects as well. And at the same time, all of this is then joined in with the actual galaxies that you see right there. They're barely visible. So all of these galaxies are connected with the gas and dark matter filament. Here's what this image looks like if you were to add all of the gas, and here's what all of this image looks like if you were to add the dark matter. So all of this is not as visible as actual stars because, you know, stars are producing light that we can easily see from really far away, but neither gas nor dark matter produce much. And so we only know, or we only suspect their existence simply by observing the effects. And one of these effects is, of course, this unusual observation that the galaxies seem to have some kind of a strange relationship and connection that causes them to act differently. And in a nutshell, the scientists behind this paper do suggest that there's this unexplained phenomenon that's causing these galaxies to behave in a very similar way. You can find out more about this by reading the paper in the description below. And the thing is, this is not the only thing the scientists have seen in the past few years. We've also observed several other things, like for example, there is an unusual alignment of quasars, or these really bright galaxies, across an even larger distance. We're talking about billions of light years. This is like thousands of more times far away than what we just looked at. And this was reported by the scientists from Belgium about 5 years ago, and the paper for this you can also find in the description below. But here what they discovered is that even on these larger scales, the actual quasars seem to have a very unusual and somewhat predictable alignment, suggesting that these unusual filaments, or whatever it is, causes the actual galaxies to kind of align, to have a very specific direction and rotation compared to other galaxies at really far away distances. There's almost no way that this happened by chance. It's almost impossible because of the amount of galaxies that they're studied, and also simply because this was a three-dimensional observation in every direction. This wasn't just in one single direction or in a single part of the universe. This was literally by looking this way and then looking that way and seeing a very similar repetitive pattern. Now, all in all, all of this kind of suggests one single thing. The entire universe is connected gravitationally and linked through these unusual formations about which we unfortunately know very little. And one of the reasons we actually do need to study dark matter in a little bit more detail and find out what exactly is happening with it, what it's made out of, and what it does to the universe is because it literally seems to have this effect on the entire universe. It controls the actual galaxies, it controls everything in the universe, and by being able to control dark matter, or at least in some way manipulate it, we might be able to find a way to control the universe. And to quote one of the characters from Frank Herbert the Dune, "He who controls the spice controls the universe," replacing the spice with the dark matter. So it's something that we need to understand if we want to one day become an interstellar and an intergalactic species. Maybe we'll succeed, maybe not. Hello wonderful person, this is Anton, and in this video we're going to be talking about a study that was able to investigate the technically most invisible part of our universe, the area known as Zona Galactica Incognita. So here on Earth, when you think about the most invisible part of the universe, you're not probably going to be thinking about what I'm about to show you. I guess in some sense it's very difficult for us to see what's right behind the sun. As a matter of fact, if this is Earth right here, the area right behind of the sun is technically invisible to us, which is why it served as a kind of a story plot for many different science fiction books. Now, that's not really what we're talking about, because we have seen that side using various telescopes that were sent over the years. However, there are parts of the universe that are, well, practically invisible to us. And although technically the farthest reaches of the universe do qualify as those invisible areas, we're talking about something a lot closer to home. So here, the area that I'm about to show you, that's essentially right there in the center of the Milky Way, behind the central bulge, is kind of invisible to us. The amount of dust and the amount of actual material facing us here prevents us from seeing what's behind. We don't really have a good picture of what might be behind all of this dust, behind all of these stars, and obviously behind the central black hole. And so we've named this area Zona Galactica Incognita. In other words, a known galaxy zone. And it's a pretty solid name, because if you were to look at the galaxy from the top, with Earth being selected right there on the bottom, right behind the bulge right there, this whole chunk of the galaxy is technically just simulated. We don't really know what stars are there. We have no idea if there are any major black holes or major pulsars or really anything. The vast amounts of dust and all of this gas that you see right here, all of this is so good at preventing us from discovering what's beyond that we didn't really hope to find it for quite a while. But it just so happens that certain parts of light spectrum can get through this dust cloud, and specifically certain parts of infrared light. And so by collecting various infrared light that's coming from those regions of the galaxy, we've eventually collected enough data to be able to analyze it and to be able to kind of see through and potentially discover certain stars. And it just so happens that Today we've advanced so much in the area of artificial intelligence and machine learning that several algorithms exist that allow us to quickly discover stars in gigabytes and terabytes of various data that we can throw at it. And so that's kind of what the scientists behind this paper that was recently published decided to do. They took an algorithm that's usually known as CNN or convolutional neural network, and they threw all of this data at it, trained it, and let it learn to recognize what certain types of stars looked like. And then by collecting all of the data from the hidden region of our galaxy, they were able to discover over 1,000 different stars we didn't really know existed. And the types of stars they've selected are the so-called Seiffert variables, about which I've talked about previously. These are stars that are really well known to us. We are kind of dependent on them because these are pulsating stars. That's what they do, literally. They increase in size and increase in luminosity, and then decrease in size, decrease in luminosity. In other words, they kind of like breathe in a sense. And by doing this breathing, and also because they're doing this with a very specific pattern, we can usually use them to determine distances in space. So this is kind of how we discover distances to nearby galaxies, for example. Here's one example from the Andromeda galaxy, and you can see that as it changes color, and as it does so periodically, we can usually determine its maximum luminosity. And by using that, we can then determine the distance to the star very, very precisely. And that's because there is a very direct relationship between how bright they get and also how often they change their luminosity. So by using these relationships, we can usually very precisely determine distances, and by finding thousands of these objects, or just over 1,000 technically, the scientists behind this paper, for the first time ever, were able to very precisely point at where these stars were located and thus show us, in some sense, what the shape of the galaxy on the other side, on the dark side, was. Now, the dark side, or I guess the far side of our galaxy, hides a lot of mysteries, and specifically related to the number of potential arms, galactic arms, but also we don't really know if there are any warps there or not. Like, for example, if we were to look at a typical spiral galaxy, this is a simulation of the Milky Way galaxy, we know that they have spiral arms, and we know that some of them are symmetric, but some of them are not. Some galaxies have disturbed or broken arms, and some of them might even have tons of arms that we didn't account for. Or maybe there are only arms on one side, whereas the other side was either disrupted or has some kind of a break, or even a sign of a collision. And so all of this is really interesting to us because it will allow us to understand how our galaxy evolved over time, what collisions with other galaxies it may have experienced, and by studying the dark side we can also pinpoint the variations in dark matter, the interactions with dark matter. We might even discover more unusual mysteries, strange supernovas, strange black holes, or strange pulsars that we've never seen before. Now obviously we don't really know what's there yet, but this is a good start. By being able to combine the infrared light that does get through the unusually thick dust clouds that we have here, and then taking the artificial intelligence or the machine learning algorithms that are already really well established and quite well understood, we can definitely discover a lot more things out there that we didn't really know existed. Now, apart from discovering the locations of these stars, that is a pretty good discovery already, the scientists behind this paper were also able to discover the ages of these different stars. They realized that the Seiffert variables on the dark side, or on the far side technically, were actually youngest closer to the center. So younger stars were closer, older stars were a lot farther. And this is reflective of what we have on our side. So technically, in that sense, the distribution of Seiffert variables is more or less the same. Now, we don't really know if there is any difference, but in a sense, maybe that's not really an exciting discovery, but it is a confirmation that maybe that's how it is. Maybe the Seiffert variables that are younger are formed near the center and they spread across the galaxy and slowly move away and then eventually end up on the outskirts. We don't know why or how this happens. We just seem to be observing this on both sides of the galaxy. But the data from the study and also follow-up studies will definitely help us discover what really is the shape of our galaxy. Right now, this is all a simulation. We don't really know what it looks like. We have no idea how many arms we have, or how many arms our galaxy has. We don't know if these arms are more or less rigid, or if they're sort of broken up into pieces. And we also don't really know if our galaxy is warped everywhere, as I've mentioned in one of the previous videos, because this is something we've discovered not so long ago, or if it's only warped on one side and the other side is more or less flat and doesn't really have any signs of collisions or any other features. Now, it's possible that in the next few months, other follow-up studies will also be able to discover other unusual objects by using a very similar technique but applying it to other types of stars. But even though this study mostly focused on the infrared light or the near-infrared light to detect the Cepheid variables, we could technically use other wavelengths of light as well, specifically the longer wavelengths. We could use radio waves, for example. And so it's very possible that in the next few years, we might be able to map this whole region very precisely by simply using these longer wavelengths of light, and then by using machine learning to try to identify these objects that were not visible to us, simple humans. And although it's unlikely we're going to discover something super unusual or super weird, or something that we didn't really expect to find, it's still interesting to map this area because, I mean, it's our own galaxy and we might need to know more about our own backyard before we try to go and explore other worlds out there. Hello wonderful person, this is Anton, and today we're talking about a new discovery coming directly from NASA of what seems to be the first ever very accurate analysis of the surface of a neutron star, also known as a pulsar. Now, you might already know a lot about pulsars and neutron stars, but in case you don't, let's go through a very brief summary. So these are exceptionally dense and extremely massive, but also somewhat small objects. Two of the most famous ones are right here. This is something that scientists back in the days won a Nobel Prize for. They're known as Taylor and Halls. And here, if you were to zoom in and just to kind of see the actual size of this object, it's sort of equivalent to a typical asteroid, and as you can see, compared to our moon, it's pretty small. But the mass here is over one mass of the sun. So in other words, it's like taking our sun and turning it into this really small object. Now, one interesting feature of every single pulsar and neutron star is that they do have very interesting dilation effects, very similar to typical black holes because of the mass and density here. And because of these effects, you can sort of see that the light is bent very close to the actual neutron star. And that also means that, first of all, if you were to look at a neutron star, it would typically appear much larger than it really is. And at the same time, you would always be able to see an object on the opposite side of the neutron star. Like, for example, right here, you'll notice that this part is actually on the opposite side, but because of the dilation effects, the light is bent, allowing you to see what's on the other side. This is kind of similar to why black holes look the way they look, or at least we believe they look like this. And here, the light you're seeing on the bottom is actually the back of the black hole. It's the disk on the other side. But anyway, generally speaking, neutron stars are either what's known as pulsars, or basically radio pulsars, radio neutron stars, where they emit a lot of radio waves, or some of them can be classified as X-ray pulsars, where they emit a lot of X-ray radiation. But for the most part, even the radio pulsars will still emit some X-ray radiation as well. And the reason they do so is because in most cases, and let's actually try to simulate this by using this large moon right next to our pulsar, when the matter falls into the neutron star, which we're going to try to simulate here, it essentially creates an accretion disk that we were able to create with the moon here, but at the same time it creates several, I guess you can call them spots on the surface of the neutron star or a pulsar. And although it's kind of difficult to see these spots in this particular simulation, we can see them much easier here from the simulation that NASA used here. And these spots form as the matter from the accretion disk, or from whatever star is nearby, or from any kind of leftover material, falls into the neutron star. But because neutron stars are so massive and also so dense and have such a strong gravity, when matter falls into them, it falls with ridiculously high velocities, up to about half the speed of light. And because of this really high speed collision, it generates a tremendous amount of energy, and usually this energy is X-rays. So in other words, we're seeing these emissions of X-rays because of the matter that crashes into the neutron star. And as you can see in this particular simulation, we were able to create a very interesting binary pulsar system with a lot of matter that's now going to be generating a lot of energy that could easily be seen from really far away. Now, if you were to ever look at the definition of a neutron star or a pulsar, you would always find yourself discovering that they seem to have these two jets, as you can see here. And these two jets are essentially pointed in opposite directions. We obviously would call them northern and southern jet because it's somewhat similar to how a northern and southern hemisphere of Earth work. And in some sense, you could even compare these X-ray spots that are generated on top of neutron stars to how our planet Earth generates its aurora or northern and southern lights through the interaction with very highly charged matter coming from the sun itself. So in some way, as you can see here, the aurora are formed by the interaction, the magnetic interaction with our planet itself. And in some sense, this is how we believe the spots here form as well, which is why they should be on two opposite sides, the northern and the southern side. However, there was this one specific pulsar that the scientists wanted to investigate using this beautiful device known as NICER. This is actually an X-ray, well, I guess you can call it telescope, that looks at X-ray radiation, and it's surprisingly located on the ISS in the International Space Station. And so when the scientists looked at the pulsar known as J0030, they've discovered something a little bit more unusual. The Earth view of this pulsar was not as we expected with two different poles. As a matter of fact, all of the X-ray radiation seemed to have been sort of concentrated around the southern pole. And there wasn't just two different emissions, there were even possibly three emissions, and some of them were unusually shaped, even crescent shaped. Two different teams investigated the same pulsar, and both teams got a somewhat similar result. Okay, it was not exactly the same, but they all had these unusual emissions coming from the southern pole, and these emissions were very different from what we actually expected to see. In other words, this particular pulsar has a tremendously weird, unusual, and inexplicable magnetic field. The way that it's formed and the way that it's emitting these X-rays is not what we thought would be possible for a neutron star. Which of course brings us to another unusual mystery that we just discovered by looking around the night skies. On top of this, we also were able to very accurately measure both the size and the mass of this pulsar, and both teams did a pretty good job at having a somewhat similar result. And what we've discovered is that this pulsar is around 26 kilometers across and has a rough mass of about 1.34 masses of the sun. So in other words, if we were to look at a typical pulsar right here, it has a somewhat higher mass of 1.8 masses of the sun, but its radius is no different from what we've discovered. In other words, what we theoretically believed their size and mass to be seems to be pretty accurate. Our theory has been more or less proven through the actual observations. But except for the size and the mass, everything else about this particular pulsar seems to be a bit of a mystery right now. Now, these are extremely important objects for us, and also very interesting objects because of their very predictable pattern of pulsation, essentially. We've even thought about using pulsars as a very accurate clock. They're technically more accurate than atomic clocks. These are the most precise pulsating devices you can find anywhere in the universe. And in the last few years, there has even been talk about how to possibly form a kind of a map of the galaxy using pulsars, because their precision and their very exact location means that we can navigate the galaxy and know exactly where we are if we discover these pulsars and can map their locations. And their pulsations are so accurate that we can then even find objects orbiting around them if we see a deviation from this pulsation. The theory behind this is that we can technically discover an asteroid in the orbit around a pulsar if we were to look at the pulsations of a typical neutron star and discover some discrepancies. As a matter of fact, the first ever exoplanets discovered were around this pulsar right here, and it has a name now. It's known as Lich. This system has 3 unusual exoplanets, and this one right here is, even to date, the smallest exoplanet ever discovered. It's about the size of our own moon and has a relatively similar mass to it, but all 3 planets here do orbit around this unusual object in the middle of the star system, the object known as Lich the Pulsar. But unfortunately, when it comes to J0030, there is really no explanation for what we're seeing just yet, because we literally just discovered this. And one of the possible explanations is, of course, in regards to the star system itself. Maybe the star system possesses some kind of object in it that's causing all of the matter to fall onto only the southern part of the pulsar. The northern part for some reason doesn't get anything. Or maybe all of the pulsars are actually unusual and have strange unusual formations on the surface. For all we know, only time will tell, but we'll definitely need to follow up on other pulsars now and try to discover what exactly they look like compared to this pulsar that we just looked at. And even in our own solar system, we know that even Earth sometimes has unusual magnetosphere anomalies, as you would call them, where the magnetic field and the magnetic lines do act slightly differently. But most importantly, even here in the solar system, we have objects like Uranus that do have unusual magnetosphere based on their rotation or their spin axis around the solar system. So here the magnetic field doesn't actually behave in the same way it does on Earth, and also has these unusual axes pointing in directions where we're having trouble explaining right now. So hopefully using these details from Uranus, we might be able to explain what's happening with this pulsar as well. Hello wonderful person, this is Anton, and as I was finishing a video on intergalactic medium where I was going to explain to you what's happening here in between galaxies, yet another interesting paper came out with a new discovery and a new picture of something that we've kind of theoretically knew existed, but never really saw in actual real life. We're going to talk about the so-called cosmic filaments and the cosmic web, and the picture that you can see right here that represents what we were able to observe in this particular study. Now, to try to explain to you why this is actually very significant and why it's a very interesting, very important picture that despite its low quality is actually a very great achievement, I need to begin right here. What you're looking at is known as the Illustris project. The link for this is in the description below, and it's actually one of the most complex ever simulations that is able to recreate universe as we believe it should be theoretically. In other words, it's a recreation of a real universe, but in computer terms. And if you follow me on Twitter, you may have seen that I posted the image you see on the screen right here. This is actually the representation of various universe simulations using various models. And Illustris right here is actually free to use, and it's absolutely amazing in what it can create. So what you're looking at here is kind of like the visual spectrum of various galaxies and technically a galactic cluster that Illustris was able to create. And here, if we look at the amount of gas that it can also generate by looking at the so-called gas density, we'll see that once in a while here, specifically if you look at the cluster from a distance, there are going to be these unusual filaments, these unusual formations that sort of connect everything together, these gas filaments that are spreading across the universe and that are technically connecting everything together, literally forming what's known as a cosmic web. Here's sort of what all of this looks like from a distance, and this is millions of light years across, with the actual galaxies being these tiny spots in the middle. And this cosmic web was always predicted, as you can see it's basically simulated in Illustris as a theoretical prediction, but unfortunately we've never really got a chance to look at it. Simply because the gas in here is so diffuse and so sort of low in density that it's almost impossible to take a picture of it, because the galaxies themselves overshadow the gas and make it almost impossible to see. In other words, we kind of always think of intergalactic space as this dark medium, but in reality there's a lot of gas here. Just as we've always believed and always calculated, most of the mass in the universe is actually here between galaxies. Most of the gas is literally stuck here and will probably never really form into anything. Now, we'll talk more about this in the intergalactic medium video, but for now what you need to understand is what we've actually discovered. So when the scientists behind the paper that you can find in the description below, this paper right here specifically, were looking around various galactic clusters, they discovered one cluster that's currently really ancient. It was actually approximately 12 billion years old when we were looking at it, so basically this was 12 billion light years away from us. And in this particular cluster, because it was so bright, the galaxies were actually much brighter than usual, they were kind of able to see certain things. Specifically, they were able to see, I guess you can call them sort of like reflections of various extremely bright galactic objects, such as, for example, the black holes in the middle of those galaxies, reflecting off the dust in between galaxies. So, in other words, imagine a really bright galactic center like the quasar that you see right here, being so bright and so exceptionally strong in luminosity that it actually starts illuminating the space nearby, and we can then detect those reflections. We can kind of start seeing the tiny reflections coming off the gas that is between those galaxies. And so this is exactly what this image here is showing us. It's showing us the reflections from this intergalactic dust, with galaxies being these tiny spots in the middle of pretty much every one of these dust formations. And you can sort of see how all of this connects everything together. So this is literally the first ever image of the so-called cosmic web. And this image is showing us what we've known all along, that the galaxies are connected with the galactic filaments, and they all form this dust web or cosmic web stretching millions and millions of light years across. These are actually some of the largest structures in the universe, forming tunnels, or I guess forming very long webs stretching for hundreds of millions of light years across. And although previously it was basically a theoretical concept that we kind of suspected existed, we now have a definitive proof, and in the future I'm sure we'll be able to use a very similar technique to discover other filaments out there that are even more visible and possibly create even better pictures. And just like the models predicted, the most active galaxies were very likely the ones that were fed the most by this cosmic web. In other words, most of the material in these very active galaxies came from inside the cosmic web, and the amount of gas around these very active galaxies was the highest. So here, by looking at the most active galaxies in this image and also some of the hotspots in the image, it becomes quite apparent that the filament or the cosmic web is responsible for feeding these galaxies. And essentially most of the materials that creates these stars in these galaxies, and of course powers the black holes in these galaxies, comes from the outside of the galaxies through this cosmic web. So it's kind of like this feeding tunnel that siphons the material into the galaxy from the outside, and that's probably how a lot of things in our own Milky Way work as well. As a matter of fact, there are a lot of suggestions that Milky Way is connected to the nearby galaxies, Large Magellanic Cloud and Small Magellanic Cloud, and there's going to be a video where I explain to you how we know this. But at the same time, we don't really have any visual proof of the connection of the Milky Way with the Andromeda, but theoretically they are also connected through these cosmic webs. Here's the problem though, these cosmic webs are really difficult to see. And the scientists in this paper were actually really lucky. They got to use one of the most powerful telescopes out there, the European Southern Observatory telescope that you see right here, and because of this they were able to find just the right region of the night sky and also just the right collection of galaxies that was active enough to illuminate the nearby hydrogen. But nevertheless, seeing this is extremely difficult, simply because the hydrogen that we see here is just very dim. It's almost invisible. As a matter of fact, the scientists believe that this is just a very small part of the entire cosmic web that's technically here. We're only seeing a tiny part of the entire web in this region, and in reality it's probably a lot more pronounced and a lot thicker than what appears to be in this image. And because galaxies like the Milky Way and the Andromeda are just not really bright enough to illuminate hydrogen nearby, we're probably never really going to see this until we develop new techniques. But in order for us to get a better image of all of this, or possibly even the image of nearby cosmic web, we would have to use some sort of a UV telescope, and more specifically UV telescope in space. Unfortunately right now the only active UV telescope is this telescope right here, AstroSat from India, but I'm not entirely sure how good its telescopic lens is, so we're not really sure if it's going to be possible to use this to image the nearby space. However, I'm sure some of the scientists in the future will probably try to use it, and we might end up with a much better picture than this. In other words, we might be able to picture the nearby space close to the Milky Way galaxy and thus see the cosmic web that connects our galaxy to the Andromeda and to everything else. But for now, that's really it. It's definitely a really awesome picture because it finally proves that cosmic web is out there, and at the same time proves a lot of our theoretical concepts as well. In the future though, we'll probably get a much better one, and hopefully sometime in the next few years. But until we get a better picture in the future, that's really it. Anyway, on that note, thank you for watching, come back tomorrow to learn something else, and watch out for that video where I explain to you what's really happening in the intergalactic space, what other things are hiding here between the galaxies. Hello wonderful person, this is Anton, and welcome to Mars. In this video, we're going to be talking about a very recently released study directly from NASA that suggests, well, actually another unexplained mystery coming from Mars. And this time, even more science suggesting that there might be life. I'm not going to say for certain that there is life, but the chances have now increased dramatically. In the last few years, NASA has very thoroughly studied the composition, the atmosphere, and a lot of other things on the planet Mars, and has discovered quite a lot of things that were unfortunately, or I guess in some sense fortunately, unexplainable. And one of those things I've actually talked about in one of the previous videos from last year, methane. We've discovered unusual emissions of methane that could not really be easily explained. And as you know, on Earth, methane kind of correlates with life. A lot of methane is produced by life, but not always. Some methane is what's known as abiotic and can be produced by various chemical reactions in the soil. And for the first time ever, we've also been able to very thoroughly analyze and study the composition of air inside the Gale crater that you see on the screen right here. And it's also the location of the Curiosity rover that's still active on Mars and is basically actively working for us, detecting all sorts of data and allows us to study the atmosphere of Mars with a lot of precision. So in the last 6 Earth years, or about 3 Mars years, we were able to use the beautiful rover to find out quite a lot of things about the Martian atmosphere. Like, for example, this is how we discovered that the surface of Mars and the Martian atmosphere is actively regulated by the CO2 atmosphere. In this case, the rover discovered that when the winter comes and when Martian surface becomes a little bit colder than usual, the CO2 gas actually gets deposited into ice directly. In other words, it goes from the gas form into the ice form. This is known as deposition. And when it becomes ice, a lot of the pressure on Mars, the air pressure, gets much lower than before. And because of this, other gases like methane and even oxygen actually go away as well. They either get deposited or disappear for some other reasons. We're not entirely sure why just yet. Then, when the summer comes, the Martian surface warms up, the ice gets sublimated or basically becomes gas again, and the released CO2 increases the air pressure, thus allowing other gases to coexist as well. And this is exactly what NASA has detected over the past 6 years. Inside the Gale crater, they've detected these changes that happen very regularly every 2 years, which is the equivalent of a Martian year. So in this image right here, you can kind of see that there's very obvious variations inside the Gale crater, and this is with oxygen and methane. So every summer there is a lot more oxygen and a lot more methane, and this correlates with the amount of CO2, and every winter it kind of drops. But this is where the mystery begins. When the scientists measured the actual values for oxygen and methane and compared them to the models that we had, basically models predicting how much of methane and oxygen there should be, they realized something was off. In the summer there was a lot more oxygen than we predicted, and in the winter the oxygen values dropped beyond the predicted values. So the actual oxygen levels were a lot more unpredictable and a lot more varied than we expected them to be. And in the last few months, what the scientists behind this particular discovery did is, first of all, go through all of the detection techniques. They double and triple checked every single apparatus, including this one right here. That's the one responsible for the gas detection. They also double and triple checked all of their data and all of their calculations. They also looked at some other models and other theoretical predictions, but just as we have it right now, there is absolutely no explanation, no physical chemical explanation to what could cause these unusual observations. Basically, the oxygen levels that we saw going too high and too low are currently kind of unexplainable. Like, for example, they mentioned that for the oxygen levels that they observed to naturally disappear and to become that low, it would actually take at least 10 years. And if all of this oxygen, extra oxygen, came from, for example, water molecules that were broken up by the sun, this was actually the first explanation they had, It would take 5 times more water than currently is on Mars for this to actually happen. So the existence of this oxygen and its ability to go to such high levels is very difficult to explain knowing what we know about Mars right now, and also knowing what we know about the composition of Gale crater. And since the amount of oxygen increased by up to about 30% from the predicted value, this is where NASA kind of started scratching its head, and they even asked for help from, well, really anyone, the public, anyone with chemical knowledge and understanding of what could cause this, because the only other explanation is, of course, is that it's life causing it, some sort of a bacteria or something else inside Martian surface that we haven't seen yet that is causing these fluctuations. And since all other gases on Mars follow a very similar pattern, including things like nitrogen and argon, all of this was detected many times, it's the unusual fluctuations of oxygen and methane that cause the most questions and the most concerns. Remember, oxygen and methane are usually gases that we associate with life here on Earth. By the way, this picture here kind of made me giggle, because this is the first thing that comes up when you look for free pictures of methane. This right here is, I believe, the study that was done in Australia in 2001, where they attached these really large canisters to sheep to try to calculate how much methane they were producing. You can probably take a guess where the methane came from. In any case, even though we do kind of want to believe that it's life, there are still a lot of other possible chemical explanations to how both methane and oxygen could be technically produced chemically by using something that's already in Martian soil and something that is not life-related. And this is where NASA is actually asking for help. They're asking for chemical experts to try to identify the reaction that could potentially produce these unusual results. Today we know that, for example, this mineral right here, olivine, does actually react with water and can produce methane. Both water and methane have a very high correlation with this particular mineral, so it could still be, unfortunately, not life-related. But the explanations we have right now are just not sufficient. As a matter of fact, to directly quote one of the scientists, this is the first time where we are seeing this interesting behavior over multiple years. We don't really understand it. For me, this is an open call to all the smart people out there who are interested in this. See what you can come up with. And this was by Melissa Trainor, one of the NASA researchers that are essentially responsible for getting all of this data. And unfortunately, other than that, we don't really know much. We know that something unusual is happening with oxygen and, of course, methane. We know that it's something we cannot currently explain chemically because we don't really understand what's happening. And we also know that this is something that we've detected several times. So it's definitely happening, and it's something that needs to be investigated. Right now, as of today, this is probably the best sign we have of life on Mars. However, NASA is being very conservative in announcing it because it could technically be a chemical reaction we just don't really understand yet, and if it's not life on Mars, it's just going to sound really embarrassing for them. But since I don't work for NASA, I can totally go ahead and say it is probably life? Aliens? I guess it is aliens. But now we need to go there and try to find them and investigate it in more detail. Hello wonderful person, this is Anton, and in this video we're going to be talking about the dangers of space. And more specifically, a recent study that discovered something a little bit scary about living in space and living in zero-G. So I think for the most part, most of you that watch this channel probably enjoy space to some extent. And I'm sure many of you, if not all of you, would love to go there one day. Even for a day, even maybe for an hour. But even though it's technically still really expensive to do, and you have to be really qualified to actually become an astronaut, one day, especially if we are successful with privatizing space exploration, it will be possible to do for everyone. But is it worth it? So in the last few years, especially since the creation of the International Space Station back in late 90s, our understanding of dangers of space has increased dramatically. Now, if I were to ask you what do you think is the most dangerous thing in space, I think most people would probably say radiation. At least most people I know. And that is true, it is quite high, and there's a lot of cosmic radiation that can technically produce a lot of damage in human body. That is not the most dangerous thing. As a matter of fact, over the years we've discovered that a lot of things go wrong with the human body when you place it in conditions in zero gravity. And so the paper that was just recently released discovered something else a little bit scary. Something that is reported right here, and we're going to briefly discuss it in this video. But let's actually summarize all of the dangers of essentially going to International Space Station and staying there for, let's just say, a few days, maybe a month. So some of these dangers begin with your vision. We've discovered over the years that pretty much most of the astronauts report either blurry vision or complete loss of vision at some point. And this most likely has something to do with the fact that gravity is required for our eyes to function correctly. Now, this is something that we may never actually overcome, and we'll probably just have to find a way to fix vision problems in astronauts if they ever occur on the way to Mars, for example. Because, for example, if suddenly one of the pilots loses his vision in the middle of a Martian mission, this could be pretty dangerous. Now, there are other problems. We've also discovered that due to the lack of gravity, the water content of our lungs begins to actually rise, and sometimes quite dramatically. Now, this doesn't mean that one day an astronaut is going to drown in their own liquid by being in space, but the danger of having liquid in your lungs is nevertheless there. It might actually damage the lungs. Although interestingly, even though water was discovered in the lungs of many astronauts, so far what we've realized is that our lungs can adapt to these situations pretty quickly, and all of them function just well. But there is another problem with lungs, and that's related to dust. In zero gravity, unfortunately, our lungs have serious problem dealing with dust, specifically the dust that gets inhaled and then deposited inside the lungs. Unfortunately, the absence of gravity allows dust to get deposited much more deeply inside the lungs and makes it really difficult to try to expel it afterwards, which could technically lead to some serious problems, an actual lung disease that could develop within, let's just say, a few months of being in space filled with dusty air that could either come from actual human skin or that could come from objects like Mars and the Moon. The lunar dust specifically could be very, very dangerous to us. It's so fine and so little that it could easily damage the lungs of astronauts living on the Moon. So in that sense, low gravity or no gravity is pretty bad news for dusty environments. We'll definitely have to come up with technologies that will allow us to clean the air very efficiently, allowing no dust to remain in it. And being in space also leads to other problems, of course, such as muscle problems, muscle weakness, and various types of vertigo and disorientation. But the scariest problem is the one that was just discovered. And that problem relates to blood flow. It seems that when the scientists behind this paper investigated 11 astronauts, they've discovered that 6 of them had a very serious problem with blood flow, where the blood inside their neck, in the so-called jugular vein, has either stopped completely or even reversed its flow. In other words, the blood was circulating in the opposite direction, which could potentially lead to some serious problems. Now, nothing has been discovered so far in terms of the actual effects of all of this, but hypothetically, an astronaut could definitely completely pass out or even die. And that is the scary part. If the blood flow stops for, let's just say, 20 seconds, or if it starts flowing in reverse for 15 to 20 seconds, the astronaut will definitely pass out. And although officially the heart is supposed to pump blood in one direction, it seems that the effects of the blood flow depend directly on the gravity. They do depend on having this force pulling on the blood channels and allowing them to create the flow in one direction. And if this problem persists, it can definitely lead to a serious brain problem, including, of course, the potential brain damage or death. So this discovery is so far one of the most worrisome, one of the scariest about the potential effects of zero-G. So does this mean that we need to stop exploring space? Well, no, absolutely not. Quite the opposite, as a matter of fact. We have to start doing even more in regards to space exploration so that we can actually discover techniques that will help us prevent all of this from happening. Because this would actually combine the various types of health studies and medicine with space exploration, it would also most likely lead to some incredible discoveries in medicine, because that's usually how it works. The discoveries that NASA made in medicine have already improved life here on Earth quite dramatically. For example, you might be already familiar that MRI machines were technically invented by NASA. Back in the 60s, a lot of the technology that came from the original space exploration missions didn't just lead to the creation of the ISS, it also led to various types of machines that we use today in medicine. And also when it comes to being in space, it's not actually all bad news. As a matter of fact, there's at least one case when being in space actually saved someone's life. James Irwin, who you can see right here, was one of the astronauts on the Apollo 15 mission that did get to land on the moon, and not just land on it, but also walk around here, collect certain types of rocks from the surface, and then bring them back to Earth. And during the mission, when the rocks were being transferred from the lunar landing module, he actually had a heart attack, or at least something resembling a heart attack, because it seems that in 0G, heart attack doesn't really affect humans with these same effects. So the arrhythmia that he had in his heart would have actually killed him if he was on Earth. But because his body was not in Earth's gravity, but instead in 0G, while at the same time receiving a huge amount of oxygen and being constantly monitored, this prevented his heart from completely giving up. The strain on his heart was no longer there, and so he was able to survive this, making him technically the first ever person to survive a heart attack in space. Although unfortunately James did eventually pass away here on Earth and was also the youngest lunar explorer to die. He was only 61 when he passed away. And so in that sense, 0G helped his heart. It saved his heart and his life. Which also suggests that maybe one day we'll find a way to treat people with heart problems by sending them to the 0G conditions in space and having them undergo various treatments there. Maybe this is how we'll solve a lot of problems that are not solvable here on Earth. And so it's actually quite exciting that in the last 20 years we were able to discover so many different things related to health sciences in space, and so many different problems that we now have to solve, while at the same time discovering things that do improve our life in space. But in order for us to continue the space mission, and in order for us to continue exploring and becoming an interstellar species, we definitely have to take our space exploration mission to the next level. And that means mission to the moon, mission to Mars, and possibly mission to other objects as well. Titan, for example. Hello wonderful person, this is Anton, and in this video we're going to be talking about a relatively recent discovery of how truly large and tremendously big our galaxy is. This new analysis finally establishes the size of our galaxy to the extent we've never really thought possible. It's actually kind of interesting that if you were to Google up size of the Milky Way, this is the result you get. Roughly around 52,000 or 53,000 light years in radius. And the same type of information will be also found in many different textbooks, and I guess in some sense it is true, but this is actually a slightly outdated version of what the galaxy is like. The cross-section here, as you can see, shows us the location of the sun, and then the galaxy kind of ends right here. In other words, all of this refers to the very easily visible part of the galaxy and ignores a large part of the galaxy known as the galactic halo that is truly incredibly large in comparison to what we see here. The best example of a typical galactic halo comes from the images of the largest galaxy we've ever discovered, IC 1101. Here, technically, I guess you can maybe call this a galaxy, but in reality the halo extends to dramatic levels. This makes this galaxy 2 million light years across and the biggest example of what's known as an elliptical galaxy with a super huge halo around it. And it's slightly easier to see it in this black and white image where you can see that the visible galaxy is definitely large, but the halo is even larger. And so our galaxy is no exception. It also has a very large halo around it, but it's obviously super difficult to see. As a matter of fact, the paper that I posted in the description below that talks about the new measurements of our size of our galaxy specifically states that it's actually kind of as if you're looking at the size of the forest by measuring everything from within, from inside the forest. It's a very difficult task, it's super difficult to do, but they managed to do it really well. And so the team behind this particular paper from Japan used the Subaru telescope with extremely sensitive cameras to try to discover the true sheer size of our galaxy. Now this is what they looked for. They looked for really bright stars and also really bright globular clusters with various variable stars, such as, for example, RR Lyra variables that you can kind of see sparkling right there in the image. These really bright blue stars sparkle, or technically change luminosity very periodically, and by knowing their periods and how luminosity changes, we can very accurately determine the distance to those objects. So they've discovered several hundred of these stars, and they looked at a tremendous amount of various globular clusters as well, and you can actually see there's quite a lot of them hiding right there in the halo of our galaxy. And by looking at all of these globular clusters and all of these Lyra stars, they discovered something unusual. Now normally you expect the so-called density of dust and stars to slowly decrease as you move away from the center of the galaxy. But there's a distance at which suddenly there's an instant drop in both density and the number of stars. And they've discovered where this happens. And it happens at a really far away distance. I'm actually going to try to help you visualize this by moving to that distance right now. The sudden drop in stars and in globular clusters happens roughly at a distance of about 522,000 light years away from the center. That's about 20 times as far away as Earth and the Sun are from the center. So that's basically somewhere right here. And that is really, really far. So this literally is the so-called limit of the galactic halo for the Milky Way galaxy. This makes our galaxy tremendously large compared to what we believed originally and what we normally think of when we think of a galaxy and its size. And what's even more interesting is that this actually makes our galaxy almost as large as the Andromeda. The biggest neighbor that we have, the Andromeda galaxy, at a distance of roughly around 2.5 million light years away from us, is just a little bit more in terms of size of its halo. The size of this galaxy is about 534,000, whereas the size of our galaxy is 522,000 light years. And also in one of the previous videos I've discussed how we may have underestimated the mass of our own galaxy, so it looks like the Milky Way is slightly smaller but more massive overall, which is actually a huge surprise when you think about it. And here I tried to recreate all of this in Universe Sandbox by using the original model of Sagittarius A star and then placing a bunch of objects that I called moons basically, each of which represents different stars and different globular clusters, just to give you an idea of how large the halo really is. So here, if we zoom into it, it's actually surprisingly a black hole. I guess I miscalculated the mass there, but this roughly gives you an idea of how tremendously large our galaxy really is. This halo is really big. There are billions of stars here. There are a lot of masses of the stars. There's obviously a lot of things like black holes. There's probably also a lot of dark matter hiding here. And we found at least 150 globular clusters in the halo of the galaxy, meaning that it's basically a tremendously massive place. But it is more dim, it's more difficult to see, so that's why the typical textbook will never really show you this. It will never really display a galaxy as something like this. It will probably just show you the typical galaxy shape that we're used to. And the other thing they discovered that's sort of interesting is that the vast majority of all of these objects that I seem to be losing now because they came too close to the galaxy is actually really old. So instead, let's use a real globular cluster from a space engine in the halo of our galaxy. So this right here has a lot of really ancient stars. Pretty much all of the stars here are at least 12 billion years old. And there's a lot of very ancient systems with a lot of ancient planets and probably a lot of ancient mysteries as well. All of these are remnants of really old events that happened in the creation of our own galaxy, probably when the smaller galaxies collided together, eventually forming the Milky Way. So all of these collisions happened approximately 12 billion years ago, and the results or the leftovers from these collisions stayed as the halo in our galaxy, while most major stars came closer and closer to the center, forming what we know as a Milky Way spiral galaxy that we have today. And so all of this suggests that around 12 billion years ago, several smaller galaxies very likely combined together. And this of course also suggests that at some point Milky Way was probably much larger before the disk was created and before it solidified as the shape that we know today. It was very likely a much larger object with a lot of diffuse matter and a lot of other ancient stars orbiting around it. Hello wonderful person, this is Anton and welcome to Saturn. Today we're going to be talking about the recent announcement that we've just discovered 20 more miniature moons around this beautiful planet, making this now the official record holder for the most moons in the solar system. So it was actually only a matter of time before we found more moons around these large, extremely exceptionally gigantic planets known as gas giants. We've actually known about various hidden moons for a very long time, and we've even discovered a few more around Jupiter back in 2017. There was a video I made back then explaining exactly what these moons were and how they were created, and why we were more likely to find a lot more relatively soon. Well, it took only 2 years, but this time it was not around Jupiter. It was around its neighbor Saturn. And although there are still, I guess, 79 known moons around Jupiter, Saturn now has 82. And what's really interesting here is that it was such a huge amount of new moons discovered by a single study. They were literally able to very accurately identify and analyze 20 specific objects around the orbit of Saturn, each of these roughly around 5 kilometers or so in size. Although some of them could actually be a little bit larger than 5 kilometers because we're not entirely certain of their current size. And as you can see from this image here, the moons are now officially divided into 3 family groups, based on their orbits around Saturn. So the closest moons that orbit in the same direction as other moons, the so-called prograde orbit, are known as the Inuit group. And the Inuit group is basically named so that we can give these moons names of Inuit gods, basically gods of Inuit mythology. And the Inuit people that you see right here have one of the richest mythologies ever. There's a lot of gods there, so there's definitely going to be a lot of really cool names we can pick. Then the second group, the Norse group, that's the largest group discovered, and all of these will be named after various Norse gods. So probably not Thor and not Freya, but some other less known gods because all of the other names have already been taken. And lastly, the smallest group is the Gaelic group, and that's the one that will be named after the Gaelic gods. Now, why do we have these 3 groups of various mythologies? Well, that's because pretty much as soon as these moons were announced, and essentially as soon as they were discovered, the Carnegie University asked for help naming them. And I'm posting the link for this contest in the description below, but basically here you have until December 6th of 2019 to propose various names based on these mythologies, and your name might get picked. Now, if you don't know anything about those mythologies, well, that's probably a good chance for you to kind of catch up on your reading and to discover either Inuit, Norse, or Gaelic mythological creature or entity or god that you would like to propose for a name for these various moons. But there are actually quite a lot of really interesting discoveries coming from this study. For one, as I mentioned, the orbit of the closest of these moons takes about 2 years. Just to give you a comparison to my favorite moon of Saturn, which is this right here, Titan, this is already pretty far away from Saturn. You can kind of see Saturn right there in the back. And a single year here, or a single orbit around Saturn, takes about 16 days. But these farther moons have a much farther distance. An orbit here takes 2 years. And just to help you visualize how far away this is, let's recreate this very briefly in Universe Inbox. So here, just for fun, I decided to name one of these moons, and it's actually from Inuit mythology, and the name is, oh my god, I'm gonna totally butcher this. Ildrivirisisong. Ildrivirisisong. That's pretty good. I think that's pretty spot on. By the way, Sedna, that's another one of the dwarf planets we have on the outskirts, is also named after Inuit gods. But anyway, so Ildrivirisisong, according to Inuit mythology, is the demon cousin of the moon. Sometimes it comes out into the night skies to dance and make people laugh. But if anyone is nearby, the people must restrain themselves, or the demon clown will dry them and eat their intestines. Right, so looks like I picked a good name. But anyway, so this really complex name is just an example of one of the names we could potentially pick for the naming of these various moons. And here, if you look at the orbit, it is really far away from Saturn itself. So there is Saturn, there is Titan, you can kind of see it in the distance, and the moon I just placed is on the outskirts, somewhere right here, and the distance here is about 1/10 of a distance of Earth to the Sun. So this is actually pretty far away. In reality, I think it's a little bit less than that, but this is kind of where some of these moons are located, so they are really far away from Saturn itself. But for the most part, they probably all look very similar to what you see on the screen here. Today we believe, based on the discovery, is that there are actually 3 much larger bodies that were probably responsible for creating these moons. Essentially what happened here was probably a very large collision between a proto-moon, or basically a much larger asteroid, that got captured by Saturn. Just based on what we're seeing here, the scientists were able to figure out how all of this very likely happened. They were probably all made from a rock slightly larger than the one you just saw. This is probably, I don't know, about 6 or so kilometers in radius, possibly a little bit more. And this was probably an asteroid or a very early protoplanet that never really got to become a planet. And this particular rock was very likely traveling through the early solar system, the so-called protoplanetary disk where all of the planets were made, and somewhere out there, somewhere in one of these gaps, was Saturn. And as it traveled through this gap, it basically got attracted to Saturn, to its gravity, but at the same time the dust in between these rings started to slow down this asteroid, and at some point it essentially got captured by Saturn itself. So in other words, it kind of looked something like this. Normally, a rock or an asteroid passing next to Saturn would most likely just experience basically a slingshot maneuver. It would do something like this. It would have its orbit bent a little bit, but would not really get captured by Saturn. For this to happen, something needs to slow it down. In other words, for this asteroid to become a moon of Saturn, as it passes close to Saturn, or as it passes really at any distance away from Saturn, it needs to have its velocity decreased. This is literally how we were able to get into orbit of Saturn with the Cassini mission, and this is pretty much how all of these moons were able to acquire these orbits as well. But how can it slow down? Well, one way of slowing down is if it starts hitting some kind of a dust field. In other words, if it flies through the protoplanetary disk of the early solar system, kind of like what you see here. So if this rock now moves through the orbit of Saturn and then starts hitting all of this dust that is still there in orbit around Saturn and also basically everywhere in the solar system, all of this dust will eventually slow this rock down to the point where it gets captured by Saturn. And this is kind of how we think all of these irregular moons of Saturn and Jupiter came to be. In other words, even though there are many moons that were created during the formation of Saturn and were even made from the same material as Saturn itself, such as for example Titan, we think Titan may have been made along with Saturn, there are still a lot of other moons that were definitely captured afterwards, specifically right after the creation of Saturn, but before the protoplanetary dust dissipated and before the solar system became the same way as it is today. And based on what we're seeing here, we think that this happened at least 3 times. So there were at least 3 separate captures, and very likely a lot more that we haven't discovered yet. And then when these larger pieces got sort of captured by Saturn and started orbiting around it, eventually they received a collision from something. Or maybe they just fell apart for some other reason. But this is literally how we believe all of these parts were formed. This is why we believe they all have very similar orbits, but at the same time they're not in a single piece. They must have collided with something else and got destroyed into tiny pieces, which suggests that it's not just maybe 20 or so moons here. It's probably thousands if not millions. It just most of them are very small to detect. And so once we're able to use a more powerful telescope, something that can resolve moons up to about 1 kilometer in size, we'll very likely end up with thousands if not millions of various moons of both Saturn and Jupiter, because that's kind of what we think is here. It's not just 79 or 82 moons, it's probably a lot more. We might need to even reclassify these because we're going to run out of names pretty quickly. Remember how a few years ago Pluto lost its status from being a planet to being a dwarf planet? Well, expect that to happen with moons pretty soon. We're probably going to have a new concept known as maybe dwarf moons or tiny moons or moons. Actually, that already exists. But it's very likely that as soon as we start discovering more than we can handle, we're going to have to completely change our understanding of what's really happening here. But for now, we don't have thousands or millions, we just have 82. And all of these were discovered using the Japanese Subaru telescope that's actually in Hawaii, and that's capable of detecting and resolving these very small objects really far away. But what's really interesting about this discovery is that it wasn't actually made recently. We had this data for a very long time. We've actually had these observations back in 2004 until 2007. But it was the use of a new algorithm that was able to discover these moons and that was able to analyze this data that allowed us to discover something that was always there. We just didn't really see it before. So the combination of new telescopes and new data analysis will definitely increase our chances of finding new objects out there in the solar system. Hello wonderful person, this is Anton, and in this video we're going to be talking about another discovery coming from the galaxy that we live in, the Milky Way. In a very recent discovery, the scientists actually found out that apparently we were kind of wrong about the mass of our own galaxy. And that's of course a little bit surprising because that's kind of like not knowing the total mass of your own home. Now, in their defense though, it's actually a lot more difficult to try to measure the mass of our own galaxy than it is to measure the mass of nearby galaxies, because basically we are somewhere right here in the middle and we're trying to observe the entire galaxy without really leaving it at all, and that's very, very challenging. Now, for the longest time we actually thought that our galaxy was a lot less massive, but turns out it's a lot more massive than we knew. Now, it doesn't mean that there's more stars. It actually doesn't mean that there's more visible mass. It's not the so-called baryonic matter we're talking about. We're talking about other mass, the invisible mass, the dark matter, the elusive dark matter that we still haven't really discovered anywhere, but we know that it's there because we see the effects. And so the scientists behind this study that you can actually find in the description below did something really interesting. They essentially used the so-called globular clusters, which is essentially the very large collections of stars, like for example this one right here, NGC 6441. So these globular clusters are relatively easy to see, and also because of this, it's relatively easy to measure their velocity. And the scientists behind this paper used the data from the Gaia Observatory that has been collecting data on billions of stars in our neighborhood and creating the three-dimensional map of nearby space around us. And this is actually some of the data that has been used to predict what's going to happen in the future. That's how accurate this data is. And it of course includes some globular clusters near us, and so they used 34 of these clusters discovered by Gaia and tracked by Gaia, but also, just to confirm their results, used 12 more globular clusters also observed and tracked by Hubble telescope. So they made sure that their data was very, very accurate. And what they discovered was that, well, basically it turns out that these globular clusters were moving faster than we expected. And because they were moving faster than we expected, but still staying within the galaxy, basically something was actually holding them within the galaxy, that only meant one thing. There's more dark matter in our galaxy than we originally believed. So they had to recalculate the assumption for the dark matter to discover a new value for the mass of the entire Milky Way. And this value now stands at approximately 1.5 trillion masses of the Sun, or potentially even higher at 2.3 trillion. That was their highest value that they've discovered so far. Now, all of this was based on the fact that when they calculated the speeds of globular clusters, they were moving at around 206 kilometers per second, way faster than expected. Meaning that our own galaxy is at least 2 to 3 times more massive than we originally thought, but more interestingly, Milky Way also seems to be potentially twice as massive as the Andromeda galaxy. And of course, for the longest time we believed that this was the opposite. We actually thought the Andromeda galaxy was twice more massive than the Milky Way. But this recent discovery suggests almost the opposite. In other words, we are currently, it seems at least, the most massive galaxy in the local region. Milky Way is literally the center of the local region, at least for now, until we discover something completely different. And I guess it's kind of fair to ask, so why is it that we keep changing these values all the time? How can we go from thinking that Andromeda was twice as massive, but now we think it's the opposite? Well, it's because of the so-called dark matter. The visible matter is actually very easy to see. Obviously, stars are relatively bright, so it's relatively easy to statistically estimate how many of them there are in the Milky Way and in the Andromeda. But this stuff is invisible. This stuff doesn't interact with anything. We don't really know how much of dark matter there is, or if it's even real. And we only see the effects, and the effects are quite obvious. And these effects tell us that, well, for the most part, in the Milky Way there seems to be more of this invisible stuff, whereas in the Andromeda there seems to be less. So the total mass of the Andromeda is thus twice less than the Milky Way. And this is actually good news, because essentially it means that we're discovering these new techniques that allow us to study the universe and space around us with a lot more accuracy than before. Using things like Gaia telescope, for example, allows us to very accurately predict motions of nearby objects. At the same time, telescopes like Hubble that have been working for decades and decades are still discovering new things even today. And with 2019 being a pretty good year for space discoveries so far, I think there's definitely going to be a lot more things that we're going to find out about the universe in the next few months. So overall, I honestly actually really love these discoveries, because it kind of redefines our understanding of everything. The science is evolving, the science is changing, and so is our knowledge, because you can't just always believe in the same thing. We're still pretty young at trying to understand the world around us, and we can't just settle for one thing. We have to always try to reinvent ourselves, and also try to change the way that we learn as well. So because the science is doing just that, I'm actually very happy at making these videos and always correcting, well, I guess you can call it mistakes, but not really, because we just didn't really know better. Yeah, of course, initially we thought that Milky Way was not as massive, and Andromeda was the giant nearby, but now we think it's the opposite. And that kind of makes us learn about everything. Hello wonderful person, this is Anton, and in this video we're going to be talking about the paper that discusses an ultramassive black hole at a distance of about 700 million light years away from our galaxy and from our planet Earth. This particular black hole is unusual in that it's most likely one of the most massive, if not the most massive, black holes ever discovered. So when it comes to black holes, specifically stellar-sized black holes, or even so-called supermassive black holes, we understand how they work for the most part. But there's one type of a black hole we don't really get, and we are not really sure how they were formed. These so-called ultramassive black holes that are usually so tremendously massive and large that they're basically a size of a typical star system. And so by looking at a region of space that's not really that well studied, the scientists were able to discover one galaxy that has basically a tremendously large ultramassive black hole that might be also the closest one to us, at a distance of around 700 million light years away from us. This would be the closest such black hole to us and would definitely require further observation. It's located in this region right here, known as Abell 85. The nebula you see is actually much closer to us, it's sort of in front of the image, but we're looking at the galactic cluster, which is of course when you have several different galaxies gravitationally bound to each other and sort of moving in the same direction. The closest cluster to us is of course the Virgo cluster. This one is much farther away. And here we have over 200 different galaxies, but the brightest one is known as Holmberg 15. This is the galaxy's image, and unfortunately that's really one of the few images out there. That's the only one I was able to find. But the scientists behind the paper right here, that you can also find in the description below, were able to very accurately discover the mass of that central black hole. And they did so by analyzing the luminosity of the central region and realizing that the closer you get to the center, the brighter and brighter things get, to the point where they're unexplainably bright. So bright, as a matter of fact, that the only explanation is a tremendously large and massive body that's producing all of this luminosity. And so by using the so-called Very Large Telescope from the European Southern Observatory, they were able to then calculate the mass to about 40 billion masses of the Sun. Now that is roughly around 5,000 times more massive than the one in the middle of our own galaxy, Sagittarius A star, and it's also approximately 7 to 8 times more massive than the very famous M87 black hole, whose photo is probably one of the most famous photos of 2019. So that particular black hole, even though it is massive, is not as exciting as the Holmberg 15A star, as it's now known, because it's essentially one of the closest record holders to our galaxy. 40 billion masses of the Sun is as close to the highest number we've ever discovered, and even that number is still not entirely confirmed. Some scientists even suggested that the black hole here might be as massive as 150 billion masses of the Sun. So this number will definitely need to be confirmed in the future, but what we know for sure is that it's at least 40 billion, and it's right there in the middle, and it's the closest one. And although that's still a little bit smaller than the largest ever black hole we discovered, which is TON 618, this one is about 66 billion masses of the Sun. It's still very impressive, especially because this is a quasar that's really far away from us. However, this is not a quasar, it's a typical galaxy, a regular galaxy, with an unexplainably massive and super large black hole in the middle, and also possibly even more massive than we currently calculated. And to help you visualize all of this, we're going to place this black hole right here in our own solar system just to see how far it reaches. There is Earth right there, that's Venus, there's Mars. Let's place it basically right here next to our Sun. But we're going to start by placing Sagittarius A star, the supermassive black hole, in the middle of our own galaxy. I think it's actually a little bit easier to see all this with a different background. So there's our Sun, it's a very small spot. There's Sagittarius A star. Here is planet Earth and its orbit. And we're now going to kind of zoom out just to see how large things will get when we increase the mass of that black hole to the mass of the newly discovered Holmberg 15A star. So here we really need to move farther back, and there you go. Its radius is around 790 astronomical units, meaning that it would swallow pretty much everything in our solar system, with maybe Sedna kind of being left behind. We can try to place the Sun a little bit farther away, with Earth being right here, and the distance between the Sun and the Earth here is just 1 astronomical unit, and this is how tremendously large this black hole is. So this right now is probably one of the more mysterious and more interesting giants we've discovered, and one of the reasons it's so mysterious is because we don't really understand how such a massive black hole could have been created. The current explanation in the paper is that it was the result of a collision of 2 ultramassive black holes from 2 different galaxies that collided sometime a few billion years ago. And although galaxies collide all the time and such explanation does make sense, it still doesn't explain how it could create such a tremendously large black hole. Specifically, how all of this resulted in what we're observing, a very bright, very active central region. And because, interestingly, for this particular galaxy, the halo of dark matter seems to orbit a lot faster than it should, with the velocity of about 750 kilometers per second, the scientists, some other scientists, assume that the mass of the black hole must be even higher. They suggested the values that are about 4 times or even more than 4 times higher than in this particular paper. In other words, whatever is happening in this galaxy is kind of a mystery, and it definitely needs to be investigated further. And even the scientists in this paper were quite surprised to find out that the expected value for this black hole is about 9 times less massive than what they've discovered. So we didn't really expect to find anything so massive right there in the middle. But since for this paper the researchers used a very well-known correlation between the X-ray radiation and also microwave radiation, and of course the total mass of the central bulge, it's possible that maybe something else is causing this. Maybe there is some kind of a event or some kind of activity behind all of this cloud of dust and stars that we just are not familiar with yet. It is possible that it's a black hole, but it's also possible that it's something we don't really understand. Because for one, we really don't understand how such a tremendously massive black hole can coexist with this galaxy. How can it actually exist in there and not basically swallow everything? And how can such a tremendously massive object still maintain a relatively quiet galaxy that we see in the middle of the galactic cluster Abell 85? So in that sense, there are still quite a lot of mysteries, but it really just means we really don't understand these ultramassive black holes at all. For one, we expect them to swallow so much material and so much dust that they should technically completely prevent a galaxy from forming any stars. They should totally and entirely reduce a galaxy to a very quiet, very dim object. But this galaxy is not dim, it's super bright, and there seems to be a lot of stuff going on in the middle. So ultramassive galaxies are definitely a huge mystery to us. And by the way, the mass of this black hole that we just discovered is very similar to the mass of the black hole in the middle of the largest galaxy ever discovered. The black hole in the middle of Holmberg 15A seems to be pretty much around the same mass and size as the black hole in IC 1101, which is a galaxy that's ridiculously large and way larger than Holmberg 15A is. So we're not entirely sure how two completely different galaxies can have two relatively similar black holes in the middle. But if the size and mass of Holmberg 15A is confirmed, or even if we are able to recalculate it to be even higher, it would definitely make this in top 3 most massive black holes ever discovered and ever confirmed. At 40 billion masses of the Sun, it's right behind IC 1101 black hole, but if its mass is higher, it might even get to the top spot. And if the scientists behind this paper are correct, it makes Holmberg 15A star the closest ultramassive black hole in the local universe detected by using Earth telescopes and observatories. In other words, it's the closest, most massive neighbor that we have. Hello wonderful person, this is Anton, and in this video we're going to be discussing the idea of the Hubble constant, the very famous constant that we use to try to establish how fast the universe is accelerating, as essentially maybe not being a constant after all. In other words, when it comes to understanding the universe, we're still kind of learning everything from scratch. So I remember when I took my first astrophysics class, I was essentially taught that the universe has this fundamental value inside of it that's predicted by Einstein's field equation. And Einstein used to refer to this as his biggest blunder because he couldn't figure it out. There was a number in his equation and it didn't make sense to him. Eventually we realized that this so-called cosmological constant could be an actual property of the universe, suggesting that our universe is accelerating with time. It's growing faster and faster and faster the more we progress through time. And this is also something that was only discovered in 1998, and the discoverers of this were awarded the Nobel Prize. Now, today we're not really talking about this. We're talking about something related to this known as the Hubble constant, or essentially the idea of measuring the speed of expansion of the universe using the constant that we've been measuring in the last few decades quite thoroughly. And to try to understand what Hubble constant means, all we need to do is basically take a look at the Milky Way right here, and then move to the Andromeda galaxy, which is roughly around 2.5 million light years away from us, with the Milky Way being this tiny galaxy you might see right there in the corner. And according to the Hubble constant, at this distance, the Andromeda galaxy is technically moving away from us at a speed of about 51 kilometers per second. That's based on the constant of 67 kilometers per second for every 3.26 million light years. So essentially, the actual space here is receding from us at this speed. 51 kilometers per second is pretty fast. But because the Andromeda galaxy is also moving really fast toward us, technically it's eventually going to catch up to us and collide with our galaxy. But because of this, a lot of other galaxies are actually moving away from us and will never come close to the Milky Way. There are very few galaxies that are moving toward the Milky Way, and the vast majority will slowly move away until they reach a point in a few billion years when we never see them again. And if you'd like to learn more about this concept, you can check out one of the videos I made previously. But what is important here is that a very recent study from only a few weeks ago, along with several other studies that have been coming out in the last year, started to discover something really unusual. The Hubble constant doesn't seem to be a constant. It seems to actually change with the location, the time, and the direction we look at. So for example, the value I mentioned previously of 67-ish kilometers per second is based on the so-called oldest light in the universe. It's based on this, the cosmic microwave background. And this is something we've always taken for granted. However, some of the other observations, for example from the nearby Large Magellanic Cloud, discovered a slightly different constant. I believe it was actually a little bit higher than that. Then we started looking around and discovered even more discrepancy. And so this paper here decided to do something completely different. They decided to just crunch the numbers, basically making it a kind of a blind study where you don't really know the answer until the end. And no matter what answer they get, they're going to publish it based on pure math, nothing else but math, no corrections. And to make sure that they were getting different results from different locations, they've taken a look at 3 gravitationally lensed quasars that are pretty well known to us and that have been very thoroughly studied already. And these quasars are all listed here, and essentially what you're looking at is something like this. It's a galaxy in front of another galaxy. The galaxy in front is much closer to us, but because of its mass, it's gravitationally lensing the light rays here, which eventually create the lens that we can then use to observe very distant objects. So there are actually 2 galaxies involved here, one being the lens, and one is the galaxy we're looking at. And the scientists behind this paper picked 3 different quasars, or 3 different very bright galaxies at a relatively far away distance from us, but all of those distances were different, and all of the lenses were different, but the actual formula used were exactly the same. So technically, if the Hubble constant is constant, they should be getting exactly the same result. But because it's essentially a blind study, the results were not available to the scientists until the end. As you can probably guess from the title, the results were extremely inconsistent. So at a distance of about 4.8 billion light years away from Earth, the closest quasar had the Hubble constant of about 82 kilometers per second. That's already way faster than what we've previously thought was possible. At a distance of about 6.8 billion light years away from us, the middle quasar had the Hubble constant of 77 kilometers per second, so a little bit lower. And at a distance of 8.8 billion light years, the farthest of the quasars had the Hubble constant of about 70 kilometers per second. So all 3 values were different, but at the same time there seems to be a pattern. The farther away we are from Earth, the lower the Hubble constant becomes, suggesting that if we were to look at another galaxy that's even farther away, it could be closer to that value we see from the cosmic background radiation. And these results suggest that the closer galaxies to us expand a lot faster than the galaxies farther away, while at the same time suggesting that with time the actual constant changed quite dramatically. As a matter of fact, it seems to have increased over time. Now that's of course a bit of a problem for cosmology, but at the same time it's a growing field, so it's expected to have these blunders. And one explanation provided so far is that, well, maybe, like the study suggests, it's not a constant after all. Maybe it's actually some sort of a particle again that is causing all of this expansion. But at the same time, it could also be a problem with our understanding of the gravity itself when it comes to really far away distances. So in other words, we might have to rework the Einstein's models and try to figure out what is it that we're getting wrong from all of these models that we have. In other words, it's actually a pretty exciting time to study cosmology because it looks like we're not really sure what's happening, and there might be a lot of interesting discoveries coming in the next few years once we figure out why it's causing all of these results to come out so different from one another. But luckily for the scientists studying this, only a week ago from when I'm making this video, this new telescope here known as DESI became operational. The telescope whose main purpose is to study very thoroughly the idea of dark energy. In late October of 2019, it had its first light, as it's called. Essentially, it was able to take the first picture just to prove that it's working and that it's going to be able to, hopefully, solve the dark energy problem. Which also suggests that maybe sometime next year, around the same time, I'll be making another video, hopefully once and for all answering the question of what exactly is this Hubble constant? Is it constant? Did we finally figure out this whole expansion of the universe thing and this whole dark energy thing? And most importantly, how all of this relates to our daily lives. Right now, it really doesn't. But then again, many things in science that we use today and take for granted today were not really that important to most people when we were just studying them. So sometime in the next few decades, we'll probably find a way to use all of this in real life as well. Hello wonderful person, this is Anton, and in this video we're going to be talking about some of the more interesting recent discoveries coming from NASA from this beautiful Parker Solar Probe. In the last few years, NASA launched quite a lot of very interesting missions, but one of the more interesting recent missions was of course the so-called Parker Solar Probe. And just like previous solar missions that NASA has launched over the years, the Parker Solar Probe is essentially meant to investigate the activity very, very close to the actual surface of the Sun. But unlike other missions that mostly are responsible for just looking at the Sun and looking at various effects, the Parker Solar Probe is of course different. And what makes Parker Solar Probe so different is of course the fact that it's going to be the closest object to the Sun that we've ever launched. In other words, unlike other probes that are just looking at the Sun, it's going to actually try to physically experience what it's like to be so close to this beautiful object. The closest approach is going to happen in December of 2024, so essentially 5 years from when I'm making this video. And if you are watching this in the future and it's December 2024, cool. Anyway, so this is what the probe sort of looks like. This is the simulation using Universe Sandbox, and this is what the Sun is going to look like when it approaches it at a distance of about 7 million kilometers, which is about 4 times closer than the distance that it currently has. In other words, it's actually going to move a little bit closer. Now, if you don't really know much about the orbital dynamics, or basically how orbits work in space, well, all you need to know is that it's going to be using Venus, which is right here as you can see, to try to lower its orbit even more than it currently has. So in other words, it's not really using any engines, it's not using any kind of fuel or very, very little fuel to try to basically move as close to the Sun as it can. Now, there's an old video I made many years ago explaining how this works. Essentially, this is known as the so-called gravity assist or the gravity slingshot maneuver, and you can see how Voyager right here used this maneuver several times to try to gain as much velocity as possible. So this is a very well-known phenomenon to us, and we usually use this for craft to use the gravity itself as a way to accelerate or decelerate instead of using actual fuel. So in about 5 years time, Parker Solar Probe is going to discover a lot of new things about the Sun, but even now NASA has already released 4 new papers describing some of the very unusual findings and very surprising findings. Now, in a nutshell, what the NASA has discovered is that this nearby space very close to the Sun is an extremely different environment as we kind of thought it would be, but not to the extent that we imagined. And in some sense, NASA even compared this to a kind of a waterfall and river phenomenon. So in other words, let's just say that somewhere right here, this is going to be Earth, and what we're seeing here, the flow of water, is basically most of the solar system. And the water itself here represents various solar wind and magnetic interaction created by our Sun. In other words, it's the flow of particles and various solar winds generated by the Sun itself. So where the probe is right now would be equivalent of this, the kind of a bottom tip of the waterfall, whereas this here would be the surface of the Sun. So it's seeing all of this extreme interaction happening in real time and has discovered some unusual properties of the solar wind so close to the Sun itself. So first of all, it discovered that the wind itself is extremely fast here. As a matter of fact, when the probe was passing through the wind, it seemed to have discovered winds that were 15 to 20 times faster than we anticipated. So the actual particles move here at up to about 50 kilometers per second velocity. And it also discovered these unusual, very kind of strange and very large waves that you can see are being formed, which the scientists refer to as a kind of a solar tsunami. So basically here it passed through these waves, through these reversal waves that were detected by the probe and were exceptionally powerful and very, very large in size. These are a type of what's known as an alpha wave, which are essentially waves formed by the interaction of various particles. This is what we thought they're going to look like, but instead they looked much larger and much more extreme. And on top of this, not only were these waves really large, there was also a lot of turbulence here, with speed suddenly changing quite dramatically. In other words, the waves themselves would suddenly accelerate or decelerate by up to about 300,000 miles per hour, or about 450,000 kilometers per hour. And all of this would happen almost instantly, within only seconds. So this is a very turbulent, extremely powerful environment. And because of these sudden unusual changes in speed, the scientists believe that maybe this is why the coronal region, this region very close to the sun, is so exceptionally hot. It's actually several thousand times hotter than the sun's surface itself. In other words, if you were to look at our sun and if you were to look at this region right here, it would be millions of degrees, as opposed to the sun's surface that's only a few thousand degrees. And so NASA scientists think that maybe it has something to do with these turbulent regions that they just discovered. They also discovered some of the more unusual properties of the way that solar wind is generated, and it seems that it's a lot more hectic and unpredictable than we thought. We thought it was kind of like more or less equivalent everywhere. It sort of spreads just like you expect the water here to spread, more or less sort of peacefully and across the entire river, whereas in reality it seems to be really hectic. There seem to be these holes all over the sun's surface that release a lot of different solar wind that does spread across the entire area and then sort of adds up to creating the solar wind that we observe here on Earth. And at the same time, so close to the sun, the solar wind also seems to be spinning with the sun. In other words, as the sun rotates, so do all of these solar particles and solar wind very close to the sun. And then eventually, as it reaches further points, that's when it separates from the sun and then begins being transmitted across the rest of the solar system. But in these close regions, several million kilometers away from the sun, it seems that everything is sort of attached and spins with the sun itself. And just like everything else in this region, it's more or less magnetically connected. So these are not gravitational connections, these are all electromagnetic connections that are formed by the very strong magnetic field so close to the sun. At the same time, it was very surprising for the scientists to discover that apart from having large emissions, like for example what we would call a solar flare, which would be very large and very easily visible from Earth, there also seem to be these really small emissions, very small flares that we never would detect otherwise. And the Parker Solar Probe was able to see these small emissions, very tiny flares that don't really affect Earth almost at all, but do produce enough emissions close to the sun, thus affecting some of the nearby regions. It might actually affect planets like Mercury and even Venus, but it doesn't really affect Earth at all. Another unusual discovery was that throughout its time close to the sun at a distance of about 24 million kilometers from the sun, the craft was actually being bombarded by various tiny particles. And NASA believes these tiny particles come from various comets and asteroids that came a little bit too close to the sun and essentially got destroyed over time. In other words, there's a lot of material that's being sort of evaporated and released from various asteroids, like this series right here that I just added in Universe Sandbox, that then produced this gas that spreads across the solar system. And the Parker Solar Probe was able to detect all of this. But the simulation I created here is actually a little bit unrealistic because the dust I added is a little bit too close to the sun. One of the major discoveries from Parker Solar Probe so far is that there seems to be a dust-free region, denoted by this ring, this orbit right here that you see. This is about 5 million kilometers away from the sun, and there's basically no dust here. Everything is or has been evaporated and destroyed, so all of this is pretty much empty of matter. Or actually the only matter that is here is coming from the sun itself, possibly things inside the solar wind. Nothing in here is from the rest of the solar system. But it's very likely that even at its closest, the solar probe will never really reach this region to explore it a little bit more. So in other words, the probe will always have a little bit of dust hitting it and will never be in dust-free region. Now, these are not the only discoveries, but I think these were some of the biggest ones, and I'm sure there will be a lot more in the next year or so as the probe gets closer and closer to the sun itself. And the reason it's going to take basically 5 years for it to reach the closest part of the orbit is because it depends on Venus to lower its orbit, and so it actually has to align its own orbit that you see in white here with the orbit of Venus that is in yellow. And so basically by timing the orbital alignments, that's when the probe gets to experience this slingshot maneuver that I mentioned previously, and that's how it gets to come closer and closer to the sun. Now, in the next 5 years, we'll probably find a lot more about the sun, but the most important part of this whole mission is, of course, for us to learn more about the solar wind and how our sun is able to generate these solar flares and everything else that affects us here on Earth. As I mentioned in one of the previous videos, I personally believe that solar flares are literally the most dangerous thing that can happen to our society today. So by studying the solar wind and how solar flares are generated, the Parker Solar Probe will hopefully allow us to find a way to prevent a serious disaster from striking planet Earth. Previously, on trying to figure out what's happening with the universe, we discovered that apparently Hubble constant may not be constant after all. Hello wonderful person, this is Anton, and in this video we're going to be talking about another cosmological blunder. An unusual new discovery coming from another paper that suggests that maybe the universe is actually also shaped differently from what we always believed. So you may have seen the video that I made previously where I talked about how some of the new observations and new calculations suggested that the universe, despite expanding, might not be expanding with the same constant velocity that we always thought. The so-called Hubble constant might not be a constant. But there was also another paper that was released around the same time that also suggested something just as controversial. And it actually relates to something that we refer to as the shape of the universe. So, okay, this is going to be kind of difficult to imagine. For us to imagine this, we have to actually imagine the 3 dimensions as a kind of a flat space, as 2 dimensions, because otherwise, I tried, it just doesn't work. So anyway, the current calculations and current understanding of the universe is that it's basically flat. In other words, if I were to take 2 parallel lines, or if I were to just take 2 really fast moving rockets and were to send them on a straight line parallel to each other moving across the universe, both of these rockets or spaceships would still travel parallel to each other even after millions and billions of years. In other words, they would never cross. That's the assumption, and that's the assumption based on very thorough calculations using some of the best data from the observations of the so-called CMB or cosmic microwave background. This is the first light in the universe and probably some of the most accurate data we can actually get. And when it comes to the actual shapes of things in the universe, or basically the fabric of space itself, we usually denote it with this letter right here, omega. Now, omega is believed to be 1. If it's smaller than 1 though, the space could be negative in its curvature. In other words, if those 2 spacecraft are still traveling across the universe, they will eventually start to slowly fly apart from each other. So the negative curvature would suggest that these 2 spaceships will eventually move away from each other, even though they're technically flying in a straight line. And then if this omega is larger than 1, you get what's known as the positive curvature. This one is a little bit easier to imagine because here it's the opposite. These 2 spaceships will eventually basically collide with each other. They'll move closer and closer to one another, even though technically they're moving in parallel lines. A while ago, NASA made this beautiful image that you see right here that explains all of this in a little bit more detail with 2 flies. So here's what all of this looks like. And up until now, we've always believed that this is what we're seeing simply based on the observations and the calculations. But there's a slight side note. With every one of those calculations and observations, there was always a certain error. But it's not really an error in observation or just being unable to see something very clearly. It's simply an error that exists there as part of the calculation in how certain we are with our results. So because of this error, we kind of made an assumption that the universe was flat. And in the most recent observations of the CMB, with the 2018 results that were being released by the ESA from its beautiful Planck telescope that you see right here, whose mission is to literally study cosmos and understand the universe, we finally got to analyze some of the most accurate data to date. And in that data, there was actually a very strange anomaly, and this anomaly was explained as the so-called A-lens. And it's not entirely clear what it's caused by, but what it suggested was that inside the observations of the CMB, the actual light was curved a little bit more than it should be. Not a lot, not a dramatic value, but just a little bit. And that value was enough for the scientists behind this paper to propose that, well, maybe what we're seeing is an actual thing. Maybe that curvature that we're observing is from the universe itself and not from the mistakes of the telescope. And just like I mentioned before, simply because we've always had a bit of an uncertainty with how flat the universe is, this doesn't really contradict previous results. It simply presents an idea that some of the observations may be explained a little bit better if we were to consider the universe not to be flat, but to be a little bit more positively shaped. In other words, having positive curvature or being basically like a spherical, ultra-large, ultra-massive ball. Now, I need to clarify something. It doesn't mean that if we look in one direction, and basically if we go into that one direction, we then are going to literally come back from the opposite direction that we're seeing. Simply because the actual curvature implied here, and also because of the actual size of the universe itself, if the universe is spherical, it's still tremendously large in size. It's much larger than we can see. The so-called visible universe, or all of the things that we actually can see simply because of the limits of the speed of light, and luckily for us in Space Engine we can even reach this so-called visible limit of the universe, because by going really fast in a single direction here, you'll eventually reach the end of the visible universe. So here's kind of what it looks like in Space Engine. Basically we have some galaxies there, and here we have empty space. Now, not to get you confused, this is not what it looks like in real life. If you were to actually travel to this location, you would not be able to tell a difference, because essentially the visible universe is formed by the location. You still get to see just as much from every location in the universe. But anyway, so at this location right now, at this visible end of the universe, if I were to look back onto the Milky Way, which should be somewhere right there, really far away right there, the actual curvature between my current location and the Milky Way would not be an actual sphere. It would possibly be a little bit more curved, but not a sphere at all, which is simply because of the actual size of the universe. The universe is much bigger than what we can actually see. We've been able to very thoroughly establish this by looking at various things in the universe, and we found that there's definitely a lot more space that we just can't see anymore. And that's of course related to the fact that the universe is expanding and a lot of galaxies are slowly disappearing and we just can't see them, simply because of the speed of light limit and because the light just doesn't reach us anymore. But anyway, let's go back to the Milky Way. So, okay, does this actually mean anything to us? Well, if this curvature is real, if the universe is technically spherical, not only does it mean that by traveling in a single direction you'll eventually look back and come back to the same place, it also means that if we can calculate this curvature, which is currently sort of beyond our capabilities, we'll be able to use that angle to maybe calculate the true size of the universe. Now, it's probably not going to happen anytime soon. We'll definitely need a lot more new telescopes and new technology to try to figure out what the actual curvature is, if it's there. But being able to finally understand how big the universe is and what its shape is in some sense existentially really important to us. We generally don't like to think of things as infinite or as being incomprehensible, and right now the universe is somewhat incomprehensible to us. So if one day we're able to use this curvature to discover what's beyond the visible universe, that's definitely going to mean that we've just reached a new level of understanding of everything out there. But once again, none of this is currently certain. Because of the actual sheer size of things we're looking at, it's still quite possible that there is an error at least somewhere in there. For this particular study, their confidence level that they're actually correct is about 99.8%. It's known as sigma 3.5 value. If you've ever taken statistics, you might remember these sigma values, and these are really important in science in general, but for this particular discovery, that's their sigma level. It's somewhere right here, so they could be about 0.1% incorrect, which might not sound like a lot, but for scientists, it is a huge deal. For typical physical discoveries, especially of course anything that we want to take for granted, the sigma level has to be 5 or more, and that's when you know it's basically almost absolutely certain. Those are the levels that physicists always agree with. But because of the smaller value here, it will take a lot longer before we can actually say for sure what the shape and of course the structure of the universe is. Nevertheless though, it's a pretty exciting discovery, it's a very interesting study, and it will possibly redefine our understanding of the universe, but also maybe create a lot of problems and a lot of arguments. And because I'm sort of the objective observer and don't really get involved in the actual arguments, it's going to be fun for me to report on this as we progress through the understanding of the universe.
Hello wonderful person, this is Anton, and in my previous experience as a teacher, I did a few conferences, I had to present a few times, and every conference I went to was, at least when you're a presenter, a little bit nerve-wracking. And so imagine a situation where you're about to present at a very important conference, and you're about to speak about your findings and how you were able to discover new things, and then you look outside and you realize there's a lot of snow. But you also get a phone call saying the conference has actually been cancelled. It's a snow day, right? Well, what do? I guess most people would probably feel a little bit relaxed, maybe go watch a movie or two, get a cup of coffee and kind of sleep in. Not this guy though. This guy decided that he wanted to continue his work, and he looked over the numbers from his previous work and decided to analyze it again. And guess what? He discovered a new dwarf planet. This guy is Dr. Scott Shepard, who was previously known as a discoverer of several other objects, including very recently an object known as Far Out. The object that, according to him, was the farthest object, thus it's called Far Out. Now, interestingly, he was about to talk about this object at this conference, and then when he was looking at his results, he actually realized there's another object even farther than this object. And so when the conference actually happened, he talked about this, but he was lost for words. He didn't really know what to say. Here was this dwarf planet that he discovered only a few months ago that was technically the farthest object we've ever found, and he just discovered a new one literally a day ago. And so he unofficially named it Far Out. Because what else would you name it, right? So that's essentially the discovery, and that's all we know about it as of today. He basically just discovered while looking at his notes right in between the snow day and the conference. Actually, we do know a few more things about it, so let me show it to you right here in Universe Sandbox. So first of all, well, here's Earth for comparison. You can kind of see it orbiting right there. Where we need to go though is much farther away. This new object is at a distance of approximately 140 astronomical units away from Earth. And I think it's much easier to visualize all of this if I actually enable orbit, so you can actually kind of see some of this stuff. There is Neptune. This is at a distance of just under 40 AU, 40 astronomical units, so 40 times the distance of Earth to the Sun. The orbit of Pluto should be this right here. And the orbit of Far Out, we don't really know yet, but we know that this is how far away it is. In other words, it is currently the farthest object we have. Now, it still doesn't mean that it's going to be always the farthest object, because objects like Sedna, for example, have such an eccentric orbit that at some point they will be really far away. But at this moment, as of 2019, Far Out, for the lack of better term for this object, is literally the most far away object we have right now. We don't really know much else about it. We don't even know its size. We don't know if it qualifies as a dwarf planet or just a very large asteroid-like rock, like for example Ultima Thule, or basically if it's a minor planet or if it's something else. All we know is that it's extremely dim, meaning that it's probably either really dark or maybe just maybe extremely small. And this is literally at the limit of what we could actually see at this distance with current technology. And the funniest thing is that it's not even the object we're looking for. Dr. Scott Shepard and a team of other scientists is actually looking for Planet 9. The mysterious Planet 9 is still something that most people are mostly interested in. And in the last few weeks, actually, there were several studies from some of the major teams. One of those studies uses a statistical analysis to try to prove that, assuming that all of our observations of other objects, for example, orbit of Sedna, orbit of Eris, and orbit of all of the other objects, including actually some of the planets in the solar system, are accidental, what would be the chance of that happening versus an actual object like Planet 9? And the chance of all of this being by accident is about 0.2%. In other words, there's about 99.8% chance that Planet 9 or something relatively massive is out there causing all of these effects. So that's kind of one good news. The other good news is that there's definitely a lot of new evidence to suggest that Planet 9 exists out there, and so these objects like Far Out and Far Out are just the sort of side effects of looking for Planet 9 and finding these incredible objects at a really far away distance. Now, there is, however, another paper that I mentioned previously in one of the videos that actually uses statistical analysis to try to find out if maybe you don't need a Planet 9, but just a very large amount of these objects like Far Out and Sedna and Eris and essentially other Kuiper Belt objects all together forming a mass of about 10 masses of Earth. If you have enough of these objects, you could potentially actually not need a Planet 9, but instead have literally billions and billions of these asteroids all over the place here, influencing each other. So that's also a possibility still. And maybe in the next decade or so, we'll be able to find out what's the real answer. For now, I'm pretty sure we're going to be finding more of these objects, because we're predicting there's a few thousands of them out there, and most likely actually close to 1 million. And so we're going to find a lot more of them, and at some point we're going to run out of cool names for these objects. So we need a better system, because naming things far out is cool, but that joke only has like this much left in it. And well, anyway, unfortunately that's really all I have to say for now. So the Planet 9 search has not finished, we're still kind of looking for it. We've discovered a really far away object, and as of today, we don't really exactly 100% know what's really happening. Is it the gravity of Kuiper Belt, or is it the gravity of a massive planet hiding out there? I hope it's a planet, of course, but you know what, sometimes the most dramatic answer is not the best. For all we know, it could be just a lot of these objects. And if so, I propose to name one of them after me, one of them after you, and one of them a wonderful planet, because that just sounds so cool.